incredibly important. These are incredibly important because I don't know about you, but I got to imagine, there's like 10% of the people who totally understand what engineering is and how you apply it. And there's 10% will never get what engineering, and when you're an engineering student, there's 10% will never get what engineering is and how you apply it. And then there's like all of us in the middle who just didn't really understand what this was. And the Capstone project to me was one of those eye-opening moments where you're like, oh, I see how all this fits together and how this works. So I think, these kind of programs are incredibly important. I really think the team for putting together, I had nothing to do with it. So I'm just in awe with how this has all come together. And I'm really happy to be here, both giving these remarks and judging. I do want to say a little bit about, one other thing I wanted to say about you guys, the students. You're going to be out in the world. You're going to go out and do whatever. You're going to go, some of you are going to go in the military. Some of you are going to go get a PhD. Some of you are going to get a master's. Some are going to go into business. I just want you to keep one thing in mind. You're going to be seeing a lot of old people like me, and you're going to think they're the mechanism that runs that organization, whatever you're doing, and they're not. You guys are the ones that are going to be run the mechanism that really gives the energy and the innovation to that organization. When I was still in a leadership position at all levels of leadership, great days for me was when I got interns and when I got second lieutenants and when I got new junior civilian employees, because that's where the lifeblood is. That's where the energy comes from. Those are the reasons that they're the people who are questioning. We think we know everything, and they ask a question. It's like the light bulb for the entire organization. So I just want to really foot stomp that. As you guys progress and move into your next step, don't be afraid to be the innovators. Don't be afraid to be the energy, because I think good organizations count on that. And if they're getting it from the top, I felt my last job, my only job was to set a broad vision for the future and then get, clear the path so all this energy could burst out and make things happen. So kind of talking about that vision, let's talk a little bit about in-space, assembly and manufacturing and servicing. I think about this in three major areas. One, of course, because of my 29 years in the Air Force, it's going to be national security, and the dynamics changed from the first 2/3 of my career to the last third of my career dramatically, from a place where, we were just eye-watering technology that, really put us, separated us as a nation from almost anyone else. I don't know if you know, but sitting here, you're sitting within a couple hundred yards of the birthplace of GPS, missile warning, reconnaissance satellites, launch. The whole thing happened within a few hundred yards of where you're sitting. So, but now the dynamics have changed. We are threatened, and we need to do things in a different way. We can't just put these big things out there. I just read this morning an article that quoted the 3-star over here, General Grant, talking about maneuver without regret, right? Those kind of things are what are really needed. And what's needed is innovative ways of servicing satellites, extending their life, being able to move them around, perhaps even, being able to launch in pieces, assemble up there, replace components that are maybe damaged, whether it's through, the increasing debris up there or other actions. All that stuff is really required. And the nation needs it because, it's a broken record, but, the dependence on our space assets as a nation is there. It's as important as the freeway system and the airports and the air traffic control and all that stuff for making things happen. So that's area number one, and it's really, really important. But it's not the only thing, right? I mean, the other thing that we're doing is revamping exploration, and with the access to space that's out there, which we'll talk a little bit more in a minute, looking really to do some pretty different things on exploring the universe. And that's also going to require all these techniques you guys are working on, whether it's a depot somewhere that you can, stop out of your way, whether it's, an ecosystem that's developed around the moon that is both for, using the moon, but also for a springboard to somewhere else. All that stuff is exactly what you all are working on. So I think that's really, again, it's your foundation that's going to be, the future of space. And finally, I'd like to talk just briefly. I spent the last third of my career, much more of my career than I thought I was going to, in launch. And launch has become dominated by commercial. We tried that in the 90s. It didn't work. And I spent my first tour in launch working through, well, how do you recover if your assumptions are bad on a program? And that resulted in some very successful launch vehicles. But now, we have two very big dominant players in space that are totally really not aligned with national security like in the past. And one is of course SpaceX. And if you go look at what their mission is, and I would encourage you to believe what they say about their mission. Their mission is making humanity interplanetary, and the first step to that to them is getting to Mars. That dynamic, has caused that company to build a huge launch vehicle that's going to go to LEO and not much else for orbital work. So sit back and think about, what does that mean for, people who are in the business of providing in-space servicing, assembly, and manufacturing. You're just going to have a ton of capability being able to launch to LEO, and then and whether you need to put it somewhere else or not, that's going to be a big deal. And then you go look at what I even find it more interesting what Jeff Bezos says his mission of his company is. If you really go and thread what he's trying to do, he basically says, we've got to, maybe we don't need to be interplanetary, but we got to do something with this planet, or else it's just going to become an industrial nightmare. And so what he says, I'm paraphrasing, is something to the effect of, I want to make Earth a big parkland. I want to move all of our heavy industry to space. That's hugely aligned with what all you are doing, and it's actually pretty exciting when I encourage you to go find what he said out in public about that. He's got a pretty interesting outlook on it, and I don't think either of them are right or wrong. I just think it's that's where they're driving to, so be aware of it. But he is also building a vehicle that is tuned for large amounts of mass to low Earth orbit. Again, just gonna really drive an industry that's around this in space this ISAM market area. So if you're looking for a vision of what you're trying to do, there's three right there. You can probably come up with a whole bunch more, but there's three big ones right there. Commercial launch industry is providing you basically a huge freight train that you can do all kinds of neat things, whether you want to make money off of it, whether you want to advance humanity, whatever you want to do. Clearly our nation is working on exploration in partnership with our allies. And then clearly, the dynamics of the national security environment have changed drastically. And this kind of technology is really going to be needed to make sure that we can continue to have an advantage from space. All right, I just want one last thing, and it's kind of a little bit in the cosmic line. I saw it in some of the charts. One thing these Capstones projects let you do is it lets you understand that the importance of program management in getting these systems developed. There are going to be development engineers that are development engineers, and they're really good at development engineers, and that's what they're going to do. There's going to be some of you that are really good at systems engineering, but a lot of times people think program management belongs to the business people, and I'm here to tell you that's absolutely not true. In my experience, the best program managers are the ones who start as engineers. So if you're finding sitting down here that you enjoy the part of this package where you're pulling everything together, where you're thinking through, can I do this on schedule? Where you're thinking through, well, maybe that requirement is the reason why this is so expensive. Where you're thinking through, well, how do I explain what we're trying to do to others? Or how do I structure a team to make this happen? That's all program management stuff. And it is hugely important. It is frankly where I spent most of my career. And I think that when you really go out there and look, the programs that technical programs that are successful, the technical companies that are successful, are led by people who were engineers by training and engineers for, the early part of their career. So I would encourage you, as you're thinking through what you liked and didn't like out of this Capstone program, don't miss the fact that you may have been liking the program management side or leadership side, and go do that. Because I think the momentum, especially early in your career, is design engineering or system engineering, and not necessarily the program management side. So that's all I have. I really appreciate. I too read these papers. I'm really impressed with them, and I'm looking forward to the briefings. Thanks very much.
Good morning. It's nice to meet. Well, I haven't met you yet, but at least I've seen you after working on this the last year or so, to see all these teams come together. But enough of that. So what I want to do, especially for people who may be tuning in for the first time, is very quickly describe what we're doing with the Cosmic Capstone Challenge. It's a national competition. We want to develop ISAM concepts. That's really like we are using you guys, the students, because of your creativity, because of your interest, to kind of come up with ideas that we may not have thought of, and to show how they can be executed. We want to help you develop into better engineers, and then eventually, if this is your field, come here, bring those ideas here. Maybe someone else would take your ideas, push them along. Maybe you'll do that yourself. And I will say that most of the teams this year have been capstone classes, but I know we have other teams that are independent study. We have some teams that are mixed undergraduate and graduate. It's not a fixed template, even if that's kind of what we started with the capstones. Okay. One thing we learned, like the second year we did this, before we were this capstone challenge, is like we're providing hands-on mentoring. We were kind of doing that because we wanted to figure out how to run a better program. And the feedback we got from the professors and the students is the best part of the program was that mentoring. And so when Cosmics, said, "Hey, we're gonna organize this," we realized we can find mentors not just from Aerospace Corporation, from all across the industry. We have 1,000 members, and because of that, we're able to have mentors, work with students at all the different universities. Sometimes they're alumni, sometimes they're local, sometimes it doesn't work out like that. But kind of having that connection, every week, talking to someone who can kind of give you that reality check. Because I know personally the team I was mentoring, they'd come in with some ideas, and I'd, you just say that's really cool, but that's not going to be effective, right? And kind of giving that little bit of guidance, so that you kind of go 5 degrees in a different direction. And I see what came out of it is the programs came out stronger. The students respond really well to it. So we emphasize that this year. This is our second event. We had a midterm showcase in December. You guys all gave 5-minute flash talks. I gotta say, I was worried everyone would go over, because I'm used to listening to professionals, maybe some professors talk, and we don't know how to talk and get a story across in 5 minutes. But I guess this is the TikTok generation. You guys are really effective. And now we're back here today. You got to really tell your story, to share what you've done, and it's great to see so many teams here today. There'll be some more tomorrow, and just as many at Goddard on Wednesday. No, can you hit me in the next slide? Okay. So this year we had 28 university teams in total. 5 of those basically only did for 1 semester. You can see there's just about 200 students total, but that number is probably a little higher than that. And again, about 2 dozen mentors. You can see our Air Force cadets there. Like Monty Greer was a mentor, and he went out there for the system requirements review. And there was other instances of that as well. Like I was at UT Arlington, the team I was mentoring, to meet them in person. I know the Cal State LA, mentors have been really hands-on and visiting and so on. So we like to see that interaction, and hopefully these connections are valuable to both the mentors and the mentees going forward in your career. Door system. Oh yeah, and so last night you guys were all practicing your stuff the last time, putting all logistics together. I was also doing last minute preparation. I was at the Dodgers game, and my older son Jordan, he's been to 5 major league games in his career, and the team he's rooting for has lost every time. So we were going to get season tickets, but he really likes the Dodgers, so he's not going to do that to him. Okay. Judging and prizes. So we're probably going to have about 15 judges. All of them are Cosmic members. We have 3 different groups from industry, government, and academia. So all groups be represented. We don't just say, come here and give us a score 0 to 100. You've seen it, the info packet, very detailed guidelines on how to score. And the point is that's a communication to the students as well on how to prepare it. We had an orientation session for them, and we're really aiming to have at least 5 judges for every team. Some will have more like 7, or most will have 7 or 8. There might be a few with a few more. The judges are doing about 11 teams each. They're all doing at least 5, and we're standardizing the scores because it's hard to get 5 judges to do 2.5 full days, and so you guys know all about standard deviations and normalization, and we're doing that to kind of make sure that we have a good, fair system. The scores, we will definitely have them tallied and reported by the end of next week. Hopefully we have it sooner, but we're not going to make promises. And we do have prizes. These are actually provided not by Cosmic, but by the Aerospace Corporation, our host today, and also where I work. But you can see there, first prize to split among your team will be $1,900. There's a second and a third, and then there's a separate prize for the best prototype, which was optional, as you guys know. Okay, so one final ask is we will send a survey out either this week or next week to all the participants. Mostly we want to hear from the students, but we also want to hear from the mentors and the advisors. In fact, we've had many meetings. Like Christoph is here. He knows I've talked to him many times about what works, what doesn't work. I know Major Miller, Angel are here as well. How do we make it more effective, right? I mean, the timing was the professor saying you can't have the outbrief in May. You have to do it basically a couple weeks before finals, right? And little things like that are important. For the students, I think it's like, what would you change? What would you keep the same, right? Like you can do a detailed critique. It can be one word. We definitely make mistakes. We want to improve the process from it. We wouldn't want to take what we had 2 years ago and still be doing it. It wouldn't be this great. We want to make it better next year. Okay, here we go. Okay, so what's coming up next year? I know for most of you, this won't affect you, but some of you may decide to do this again. I already had one student ask me, are they allowed to do it again? I'm like, sure, that'd be awesome. We would love to see student clubs kind of take up the mantle of this and have that continuity year to year. Next year, there's going to be 4 different tracks. This year, we just had 1 track, and I'll explain those in a minute. We'll continue to have the mentors. We're gonna cap it at 100 teams. I mean, logistically, 23 is hard enough. 100, someone else is going to be in charge of the logistics beyond me, certainly. But then we figured 100 teams. We have 1,000 Cosmic members. I think we can get 10% of those members to mentor a team. We had about 25 this year, and we started late, so I think we can do that. Open to any team of students studying at a U.S.-based university. You don't have to be U.S. citizen. Like I know today there are students here who are not citizens or not green card holders. You can participate as long as you're studying at a university, and you can also work across universities. If you want to, like we haven't had anyone do it yet, but I think that would be great. Schedule. Oh yeah, I didn't finish writing the schedule down, but I will say that we're going to we've completed the preview release and we're going through the process to actually get that so we can send it out to everyone. And that will come out this week or next week again. Early registration. In fact, I already opened up a website. It's more for universities than students, but if you have a student club, it's fine. Where you say, hey, we want to do this next year. Next year, we're going to have 2 teams from Cal State LA or 5 teams from Penn State or whatever the number is, so we can start planning for that. Again, we'll have the midterm showcase the week of December 8th. We'll have the final showcase. I think it's April 13th next year, that same week. We might add one more thing on there, which would just be a short report of recommended references. We did that this year very off the cuff, but it might be a good improvement. Next. Oh, there we go. Okay. So what are the tracks for next year? What are we changing? Like track 1 looks a lot like what we had this year. Instead of being on the BCT bus, it will be on the bosun's locker, which is basically going to attach to the ArcAssist port, which is a persistent platform in space for doing development tests. So that's exactly what we want to do. Noah Glad and Dave Barnhart are all on board. In fact, the question we got more than any other this year is like, how can we get CAD of the bus? And it's like, well, you can't get it because Blue Canyon wouldn't release it, right, without an NDA, and that doesn't help. So this year, they basically designed a box to put the experiment in. They're defining the interfaces, the power requirements, and so on. So it's gonna be really addressing a lot of the issues we had with the main track. Track 2, it's a lot like track 1, except instead of doing it on orbit, let's do it on the moon. Right now, we kind of have the Blue Ghost payload space as a placeholder. That may change as we refine it. On track 2, we're going to say there's a prototype required, right? Like this year, a prototype was optional. It's still optional next year for most of the tracks, but one track we're going to have a prototype required. So if that's a big part of your program, that may be a better fit. Track 3. Now this one came straight from the Space Force. I think Lieutenant Zarek is online actually, and instead of just coming up with a process you're going to do, it's almost an architectural level process. Think about designing a modular maintainable spacecraft that can autonomously service multiple client satellites and kind of maintain themselves. We floated the idea of like basing it on ESPA Star, which is basically can hold 8 different payloads, and then you can use those modularly, but it's open to something else. And again, Andy Quas of Northrop Grumman has been instrumental in describing that. There's a lot of detail in the preview release. We'll see next week. And then the last one came from NASA Ames, from Greenfield Trin and Olivia Formoso, which is, if you guys have seen Armadas, you may have it basically constructs large truss structures, but they have other robotic assembly methods. So what they want to think of is like, hey, don't think so much about fitting it in the box. Think about the structures you can make. Think about the infrastructure you can make on the moon, in orbit, on Mars, and what will that do? Are you going to build a large aperture? Are you going to build a large like container of something? We'll define it as we go. And so I was going to say on track 3, the distinguishing there is I think that's a little more complex. That one's really geared more towards people who are looking at space systems. The other ones I think are good for any mechanical or aerospace engineer. Track 3, well, I also think it's more complex. I think if you're a larger team, that kind of gives more room for larger teams to work. So we said if you have 10 or more people on your team and you want to compete for the prizes, you should do track 3. But anyone can still go after any of them. Yeah, and I think that's it. We have 3 minutes, so we're going to start at 8:45. I put some references up there that myself, other members of this team, as well as some of the past teams from the ICM Design Challenge published. And yeah, and I will say before I turn it over to first team from Cal State LA is after you guys, you should stand at the podium so you're on camera. But if you want to walk around, that's fine. We can adapt. After you complete your presentation, after the questions, You're gonna have 24 minutes to brief. There'll be 4 minutes for judges to ask the questions. If there's remaining time, if there's remaining time, we may take questions from the audience, and then we'll have 2 minutes for the judges to record the score. During those 2 minutes, we would like to get a posed photo for each team at the top. If your mentor or your advisor is here, they're welcome to join you. Yeah, I think that's it. So with that, we're gonna get started with the first team. That's Free Flyer Grappler from Cal State LA.
Perfect. And then are we ready to start then? Are we gonna start? Perfect. Cool. So, good morning, everybody. My name is Michael Morales.
Good morning. My name is Jordan Sabol.
My name is Alessandro Gutierrez. And my name is Brian Hernandez.
And we are the Free Flyer Grapple system at California State University, Los Angeles. Cool. And then Brian will be introducing the background and objective.
So to start things off, this is our team. We comprise of 7 members. We have 6 mechanical engineers and 1 electrical engineer. And then for our project background, we are to utilize the Venus satellite and design a system, a grapple system that can be applicable universally, despite any mission requirements that is used for. And the purpose of it is that it's supposed to be done all autonomously using as many chain orders as needed. And the purpose of it is to increase the lifespan of the operations of a satellite and to decrease or minimize space debris. In here, we will display some of our deliverables asked by our client. So some of the things include providing research behind our project, the concept designs, a detailed model of our chosen design, the calculations to go along with it, and computer vision. And as you can see on screen, that is the model of the concept design that we chose. And now for system overview by Michael.
Perfect. Thank you. All right. So before we start, I would say that we're going to go over some of the requirements, the chain of commands, and also the 3 main components of our design that help us achieve our commands. So on this slide right here, we have the requirements. Here's just some of that we needed in order to help us with our design criteria. The main were the locking mechanism, attaching, capture envelope, and also the preload and release. This is just some of the objectives that we had for our design, the source of requirement from our client, and also the method of verification, which is designing, analysis, and also testing. For the chain of commands, so there's the top three that we wanted is we make sure was to capture, release, and then of course locking. So we have 5 in total, which is approach phase, alignment phase, and capture phase, post capture phase, and release phase. The design components, of course, consist of the umbrella, the locking tabs, and springs that help us with the top 3, which is capturing, locking, and then releasing. And then I'll be introducing Antonio with the mechanical design.
Thank you. So what I'm going to be going over in this slide and the following slides is essentially the final iteration of the design that we ended up going with and some of the concepts that we went with. So starting off with the final iteration with the design that we do currently have, we have the active vehicle, which is consisted of 2 motors, one motor, which is going to be driving the grapple mechanism, and the other motor, which is going to be driving the locking tabs. We do have 3 passive springs, which is essentially going to be used to push away, once the mission is complete, push away the passive vehicle. So here are some of the design concepts that we ended up starting with, each with different components, trying to meet as much of the requirements as possible. And we had in the next slide, we're going to be showing some of the method that we utilize to help narrow down the final iteration. So this is a decision matrix with the weighted distribution. The weighted distribution assisted us in prioritizing what was most important based off what the client needed. And we have it color coded, green being the best, yellow being okay, and red being for the worst. The biggest takeaways or key points from this chart that we used was we saw design 1 and design 4 having the most points. So what we ended up using was the locking and alignment feature from design 1. We use that, and design 4, which is the capture, we use the umbrella design. So I'm going to be passing it back to Michael, who's going to be going over the design subcomponents.
So we'll be talking about the design subcomponents for the grapple system, the locking tabs, and also the springs. So this is some of the design iterations for the umbrella design. As you can see on the left, we have the design concept for umbrella design 1. And then on the right, we have our current design concept, which we have right now. On the right, you can see that we have just 1 lead screw going in the middle. That's helping us with controlling all 4 arms, and also there's pivots on there. It's for once it captures, there's more friction in there, so it doesn't move at all. The next one is design iterations for the locking tabs. On the left, we can see that the first iteration that we have, and then this is our current design on the right. The left, as you can see here, is much different because in the middle we do have a motor that will help lock these tabs. And then for the springs, design iterations for the springs, we have on the left, which was 1 big spring in the middle, that would help push and release the system. And then on the right, we had to change that due to the fact that our grapple system would be in the middle. And now what we solved or designed was to have 3 springs around the system that would help push once it disengaged. And then now I'll be handing it over to Jordan, who will talk about the computer vision part.
Okay, so for the computer vision portion, it kind of ties into the autonomy that will be helpful in our project. A little bit over about what's going on next is how a little bit into detail the first chain of commands, the approach phase, and then talking a little bit about the software that I used, and then a little bit into the coding that was used. So to be fully autonomous, while it is approaching, capturing, and releasing, the grapple system will be operating without any outside interference. We decided to go with Aruka markers, which are simple, they're scalable, and they're not easily distorted. And the approach phase is the beginning of the chain commands, where we will be monitoring the distance, the trajectory, and the speed. So the distance is basically how the overall distance between the active and the passive object. The trajectory is kind of like the angle that it's coming at, because we need it to be coming at a correct angle, and the speed is just how fast it's approaching. So for the software, I use Visual Studio, which is a code editor and a debugger. In my program language of choice is Python because of its extensive libraries, mainly OpenCV, which is Open Computer Vision, and within Open Computer Vision, we use the Aruco libraries. So for the target detection portion of the coding, instead of just talking to you and showing you guys the code, I'll just explain a little bit about what it is. So first, we need to generate the Aruco markers, which is the size, and each Aruco marker has an individual ID. And in order to detect that, we need another code, which is the Aruco marker detection, which will basically read each individual Aruco marker and be able to identify its individual ID. And then following that, we need to calibrate the camera that we're going to be using in order to accurately determine the distance. And then finally, we have the Aruco marker distance check, which will basically determine the distance from the camera to the Aruco marker that it's reading. And following up would be the electrical portion by Brian.
Okay, to start things off for the electrical portion, I'd like to discuss the motor that we selected and why we selected it. So the motor that we use for our reference is the NEMA 23 stepper motor. We chose this specific motor due to its high torque capabilities. We calculated how much torque is needed from both the umbrella system and by the tab system. Taking whichever value was bigger, we doubled it to account for worst case scenarios. And this stepper motor goes beyond that. So we chose this. This is also a DC motor for reasons relating to the Venus satellite. It already exists in a DC system. So keeping it in the same system makes hooking this up a lot easier with a lot less electronic parts needed that could potentially mess things up along the way. And the other different types of why we chose this motor is due to its precision and how simplistic it is. The next thing is a sensor that we chose. So because this whole system is autonomous, there needed to be a way to tell the system, we made first contact, move on to the next step. So when our active portion and the passive portion make contact, we chose a force sensitive resistor, which simply just when force is applied, resistance change. In this case, that change will allow our autonomous system to know that it's made contact and to move on to the next phase. We chose this because of how simple it is and how unobtrusive it is in our entire design philosophy. And because of its simplicity, there's a lot less things to go wrong, like interference with the sun. Now for discharge, this is one of the big requirements that was asked by our client. And we went into two routes of how to go about discharging. The first route is upon first contact, discharge is moved from our grapple system through the arm and onto the satellite, in which it would get dispersed across the main body of the satellite. And the second method is what's on screen right now, which is the plasma contactor unit. This was published by NASA in 2016, or released in 2016. And this currently operates on the ISS, and its purpose is to exist on the passive object, and periodically it would pass charge through a couple loops in which plasma gets dispensed, thus discharging the system entirely. And here we have the schematic for our motors. So doing a couple calculations, we determined that our motor needed 24 volts, in which the Venus satellite can accommodate 24 volts. It goes directly to a driver to tell the motor what to do. And to give the driver commands, it's also attached to a microcontroller. And even though it's we represented here, the button and the potentiometer is merely just supposed to be a digital representation, as all about this is going to be digitally controlled by the microcontroller. The potentiometer is meant to reduce or increase the RPM of the motor, while the button's purpose is to open or close the umbrella and unlock and lock the tab system. And lastly, to break this down a little further, here's how everything so far relates to each other. So we have our marker that exists on the passive object. We have a camera to look for that marker. Once it detects it, the code will automatically start the alignment and grappling phase. Upon first contact, the force-sensitive resistor will tell the system we made first contact, begin the soft capture phase. The umbrella will deploy by the first motor. Once that's completed, the second motor will begin to lock the tabs, thus completing the locking phase of our system. And now I'll be handing over to Antonio for data and calculations.
So for the calculations, what I'm going to be going over is essentially how we ended up determining the stepper motor for our application. So starting off with some spring calculations, what we were trying to calculate for here was the maximum compression, and communicating with our design team, we ended up getting number of coils of being 5, wire diameter being 1/4 of an inch, multiplying those. We got the maximum compression of 0.0318 meters. So now to calculate for the spring constant, we ended up using the previous value and using some other values that was given to us from Cosmic, in this case, the Venus bus satellite, 70 kilograms. The separation velocity, that was the feature that our clients did want it to be, which was 1 foot per second. Plugging them into our equation, we ended up getting a spring constant of 12,902 Newton meters. Now, for here, we're calculating for the total or the forces that are acting on the ball screw. And we can see on the free body diagram, there's an actual load that is going to be acting on when it is lifting the Venus bus satellite or lowering it. So we ended up calculating or using the 70 kilograms, which is a mass, multiplying by Earth's gravity. We use Earth's gravity just for worst case scenario, and also mainly so we could conduct testings here. That value came out to 154 pound force. And then using the spring force that was calculated, we added that to get the total actual force of 509 pound force. So for this slide, we ended up calculating the total torque that is being applied on the ball screw. And these equations were gathered from the machinery's handbook. Same thing for some of the variables or values. So first, we ended up calculating for the total torque required to turn the thrust collar, which in this case was 1 pound inch. For the screw torque required to lift the load, 6.94. Adding those, we got 0.9 Newton meters. Now, what this value is telling us, and connecting it back to what Brian was saying, the NEMA 23 stepper motor, that has a holding torque of 2.43 Newton meters. So this is well below, which is essentially what we want. And the reason being is when it does come to finalizing the capturing phase, we don't want it to over rotate after. And now I'm going to be passing on to Jordan, who's going to be talking over about the conclusion.
So just to wrap things up here in our conclusion, we're just going to be going over some of the technology gaps that we noticed and what we learned overall during our project phase. So the main points is being that managing the energy consumption that will be used from all the autonomous components, because they're going to always need to be active, might be an issue. Another one is the accurate testing or simulation of the autonomous grappling system here on Earth because of the no gravity conditions in space, and the little to no remote communication between ground and space, since it's mainly going to be autonomous. And then our team went through a lot of concept designs to end up using the umbrella capture system and the locking tabs. We learned very early on that communication was very important. And the next steps we like to do is 3D print our prototype for the Grapple system. Questions?
Okay, we have time for questions, so I want to offer that to our judges first.
You guys, oh, go ahead.
Did you chose I believe it was a six-sided grapple fixture for alignment, the where the tabs are. I'm curious why you chose the 6 versus some other number, specifically not an odd number. Okay.
So I believe. Good question. We went with just the 6 just because on our previous design that we had before, we wanted to just do just a full 6 just for to see if we can lock it and make sure that we don't miss any once it approaches, it's so that if we were to miss or at least have or if we were to miss a little bit or misalign just a little bit, it has more room and more clearance to actually get inside of it more than compared to like a different like 4 sides or 3 sides of for the hexagon.
Thanks for the presentation. Can you hear me okay?
Yeah.
Does you talked about alignment.
Mhm.
Is there a specific clocking orientation, or is it agnostic to, whether it's aligned with your fiducial or it's 30 degrees off, 60 degrees off, all the way around the clock?
Yeah, so for that we had talked about this before. We mean talking about more of like how the fiducial would be aligned. So if the way how the fiducial recognize the fiducial, it should be aligned to it. In case of any scenario that it wasn't or if it was off, those that alignment feature should help, which is a 6-sided hexagon, should help with it align a little bit better for it. But her fiducial should help us out more.
Yeah, just to add a little bit more. The point of the fiducial and the autonomous and the point of the fiducial and the autonomous and the coding is to set up the approach for the best case scenario. I know that may not always happen, but that's that's what we have the code to have, basically the best approach for it, and then we hope, or then we expect the alignment geometry to help like realign the rest of the connection.
Okay, thank you.
I had a question related to that. Do you guys mind going back to that slide where you guys have the weightings for the trades?
This one?
Yeah, thanks. My question is kind of related to this, but not really. But do you guys have an idea of the misalignment tolerance that the mechanism has for like the capture envelope?
We don't at the moment. We don't at the moment currently.
Okay, got it. Thanks. How did you guys compare the alignment for all the different versions then?
Yeah. Okay. So the way we kind of did it was just we sat together as a team. We sat together with the team and then with our advisor, and we kind of just some of these models or concepts were actually modeled up, and we did like a what is it, a motion analysis just to see how it would interact with the passive and active vehicle. And we noticed that the design 4 and design 1 were, out of all the other ones, had kind of met a majority of the requirements. But that's essentially how we ended up doing the checking to see if they would align properly or not.
Got it. Thank you.
Okay, do any of the other judges have questions?
Yeah, I have a question. I was just wondering what kind of consideration you guys gave to the environmental impacts on algorithms or materials. Like you have use of a lot of different springs, so they'd behave differently in different temperatures. So thermal regulation, or with the computer vision and the fiducial markers, the lighting conditions can change depending on how fast things are rotating. So I just wanted to hear your thoughts there.
Yeah, we do have it in a backup slides. We just so I guess as for considering for materials, we were referencing a lot of the NASA articles. I think in this case it was NASA standard 6016, and but for some of the when it came to selecting some of the components, where is it at? So yeah, so NASA standard ended up stating they had a set of requirements themselves, which I believe was 13. But we focused on a small focus area, which connected to our overall requirements. One being the corrosion resistance, thermal stability protection, resist temp fluctuations, and the remaining three. And from those three, we kind of gathered this table, kind of just highlighting like the biggest things for the materials. And for in this case, the 5000 series of aluminum alloys, once it reaches a certain temperature, it's going to be stress due to stress corrosion. It's going to be sensitive, so it could become brittle. And same thing like for the 300 series. So what we were looking at was trying to see what would be the best for our application. And we noticed the titanium 6 AI 4V was one of the tops. And yeah.
Okay, great. Yeah, I'm glad I asked that and see that you have this in the backup slides. Maybe some of this in the actual slides would have been good.
Yeah, and just to address what you also mentioned about the fiducial and the code, I chose to go with the Aruka markers for that purpose because of how simple it is and how well it can still be recognized despite it being at a slight angle, or maybe if there's like a glare from the sun or any shadows that
Okay.
may be induced. Yeah, thank you.
All right, great. Thanks.
Okay, do we have any more questions from the judges? Since we have a couple minutes, I'll ask if there's anyone in the room who has a question, you can walk up to the mic. Okay, I think we can thank our speakers again, and maybe walk to the front of the stage and we'll get a quick photo. Okay, we'll just take a minute here while we get the next slides pull up. But the next team is the U.S. Air Force Academy Astro team. Maybe you can get a picture of them walking in or walking up too. Act natural. Okay. We're gonna wait till we get to 9:15 to start, but you can walk up here now. We're just gonna stay right on schedule. I shouldn't do this, but since we have a couple minutes, what was your favorite part about the beach yesterday?
Volleyball.
How'd you know we went to the beach?
You know, the Navy SEALs do a little thing called the sugar cookie. So you go into the water, you come out, you roll in the sand, and then you go back into the water. We didn't. That was fun.
He was the only one that did it.
Not all of us took in that, so you know.
So you said wait till 9:15. All right, so good morning, everyone. We are the team from the United States Air Force Academy, and we are really excited today to present our conceptual design review for SPAMM, or the Space Printer for the Autonomous Manufacture of Megastructures. Quick team overview. I'm the project manager, Stephen Timperley.
I'm Grant Steck.
I'm Gio Simoncioni.
I'm Nick Rayolio.
I'm John Fredette.
I'm Gavin Eric.
I'm Ashley Spear.
I'm Benjamin Yan.
Oh, sorry. And then our mentor is Dr. Monty Greer, and our advisor is Major Daniel Miller. Just a quick outline of what we will be talking about today. There's a lot to get through, so we are going to go fast. Next slide. Just quickly looking at our system engineering milestones, we identified our project manager pretty early, selected our operations pretty early as well, presented our SRR, completed our trade studies, presented our conceptual design review to our mentor, developed a plan to reach our PDR, and today we are presenting at our C3 final showcase.
All right, we're going to get into a lot of details, but before we get into all that, I want to let everyone know our big picture stuff. So things to keep in the back of your mind as you look through all the details we have here. Before we even started our brainstorming and coming up with our design, we asked ourselves, what does the future of space look like? And we really embraced all that sci-fi.
Sorry, guys. I wanted to
big,
just point out we can't see the presentation, so online.
It's showing slide 19, which is your references slide.
Somebody can help you guys. All right. Yeah, we're seeing this now. Great.
Can everyone see the executive summary slide?
Yep.
Yes.
All right. Like I was saying, we really embraced that sci-fi nature, being able to build megastructures in space. All right. Being able to build a lot of things and be able to build big things. And we identified the main roadblock in this getting from where we are now and getting to there as the launch constraints. And so we decided to build something that would bypass those launch constraints. The Space Printer for Autonomous Manufacture of Megastructures, or SPAMM. This will be able to print objects, move along those objects, and print indefinitely large objects.
Okay, so what does SPAMM look like? So when we're looking at SPAMM and its main three operations, we see FDM 3D printing or fused step addition modeling 3D printing,
utilizing a robotic arm. This includes things like heating, extruding, and our printer head movement. Our mobility across manufactured parts, which includes things like moving along tracks and switching along those tracks. Our leveling and location estimation. This is determining our part location and then moving across that part and continuing the print. An important note is we will be reload capable. However, this will not be part of our main mission.
All right, so now we're going to be looking into our business case and more particularly our capabilities and what we're going to be able to apply this to in the future. So our system can create a lot of unique structures in the vacuum of space. And to illustrate this raw capability, we're able to create a 10 by 10 centimeter beam, 1 kilometer at 10% infill every year. And this is assuming a 2 millimeter nozzle and a 41.6 millimeter per cubed per second flow rate. And some specific applications that we can do is one, deployables, which allows us to house different infrastructures like trusses, antennas, different solar arrays, and apertures, and be able to push it out as a deployable. And some other pressurized and unpressurized volumes like fuel tanks, space habitats to support the mission, unpressurized volumes like storage and radiation shielding, and lastly, really interesting, spacecraft, which allows us to create and repair in the ever-changing environment of space.
Cool. So regarding our launch and orbit, we're going to be 3D printing in space, which, as you can imagine, probably takes a little bit of power. So our consideration for that, placed our orbit into sun synchronous with an inclination of 98 degrees. This ensures continuous sun from August to February. And when we don't have continuous sun, there is minimal in shadow time. So there's really not any concern about being able to print continuously, or at least heat the filament continuously. Additionally, we want our objects to be able to deorbit within the 5-year standard set by the FCC, which is why our orbit is in low Earth orbit, 600-kilometer circular orbit. And this from SMAD says that all of our parts and our satellite should deorbit within 2.6 years after mission end of life. And finally, in terms of communications with the ground station, since we're in such a high inclination orbit, really the ground station was selected arbitrarily. We propagated out the simulation for 2 years, and no matter what ground station we chose, we've got pretty consistent contact times, 4 to 5 times a day, 7-minute minimum contact window. And in order to achieve this orbit, we'll be launching out of Vandenberg Space Force Base due to its capability of placing satellites into polar orbits. And we'll be using a Falcon 9 rideshare to LEO, which is ESPA capable as the Venus BCT class bus is. Slide, please. Cool. This is kind of our operations overview. So once SPAMM is situated in its orbit, it will receive G code, which is the print code from the ground station. Again, we arbitrarily chose Cana Point. Now, we have a 1 gigabit per second upload rate on the Venus BCT class bus. We're assuming a maximum file size of 100 megabytes, which if you do the math on that, it takes less than a second to transfer a very large file size to the satellite. So contact time with ground station should not be an issue for receiving all of this code for the print. Now, once SPAMM has verified the file integrity, has ensured that we have proper attitude and sufficient power to print, we will begin printing. We are estimated to be capable, as mentioned earlier, of printing a 1 kilometer long, 10 by 10 centimeter beam at 10% infill for every full year of operation. Additionally, we'll be capable of printing or at least heating the filament while we're out of sun. And finally, once our print is completed, it will be detached from SPAMM and will deorbit within around 2.6 years. And SPAMM will be free to receive the next print code and begin printing again.
All right, so one really crucial step in establishing this system was exactly how are we going to maneuver this printer. So we looked at 4 different methods of maneuverability. One, a climbing bot, which uses bipedal climbing to maneuver, a roller bot, which uses wheels to maneuver, a hybrid between these two with climbing functioning and grappling functioning, and then a thruster-based printer. And as you can see, we use different criteria like structure and complexity, degrees of freedom of each system, ease of orientation and gripping stability, and we applied colors to each of these qualities to signify what we thought would be best for this environment. And we ended up deciding on this hybrid because of its versatility and because things like degrees of freedom was really conducive for this mission, ease of orientation in space, and then the gripping stability to our structures.
So yeah, here's a CAD model of what SPAMM will actually look like and a conceptual animation of how these operations will combine to achieve mobility across manufactured parts. Don't start the video yet, but we have an example on the right of what this would look like for printing a structure such as a square beam. So the rail would be represented on top and the structure on the bottom, even though they would still be printed with the same material. Go ahead and start the video. So here we have our whole model. We just remove the solar panel array just for visualization. It's a robotic extruding arm and the maneuver and legs, which allow SPAMM to actually be attached to the part. And this shows how that will be achieved just by this gear subsystem on the side of the rail. This is how it will actually print each section. Of course, it's simplified just to show how it can achieve mobility in the X, Y, and Z direction. So here you can see how it can move along the X axis infinitely. It will now print a curved part to show how it can maneuver now anywhere in the XY plane. And this blue plate you see at the bottom of the rail just represents any kind of structure that can be printed beneath the rail. Now it will print a vertical piece to show how it can move positively in the Z direction just by detaching that gear subsystem and then reattaching it. And we'll print another 90-degree section at the top just to show how it can now go in the negative Z-axis as well, just going down along that part. Sweet. And then finally, you'll see it print another track parallel to the current track just to show a track switching capability, which would be utilized if SPAMM were doing any repairs on an existing structure or just had to loop around on a section that was already pre-built. And there we go. Slide.
Okay, so what do SPAMM's overall concept of operations look like? When we're ready to print something, we're going to send the command to print. Our bus will then verify sufficient power, stable attitude, and correct timing. Then we'll relay that G code, which is our print file, and then determine if we have this seed or initial print segment attached and provided. If we do, then we'll go right into leveling and localizing ourselves on that track and continuing into our printing loop where we extrude our polymer, move our robotic arm and the printer head around, and move across that track. And if at any stage is needed, we'll have the capability to reload that filament. And then when the part is finished, we can detach from the part and then reset to our initial configuration, ready to print more tracks and things like that.
All right, so now we're going to go over how our payload is going to fit with the provided Blue Canyon Technologies XSAT Venus class bus. First off, power. The bus provides 440 watts of power. We are expecting to use around 220 watts in sunlight to have full printer operation. This breakdown is going to look like 150 watts for printer operation and 50 watts for all those robotic arms you saw in the animation. About 70 watts will be for filament heating, making sure we have good thermal environment and that we're not having filament come too cold or too hot, preventing jamming and cracking. And the rest of that 80 watts will be the other printer operations, such as extruding and moving that printer around. In Eclipse, we're going to be using just that printer heating to make sure we have a good thermal environment. In the rare cases, we are in Eclipse, just because we're in that sun-synchronous orbit. Volume, we are provided with a 17 by 16.4 by 27 payload volume. You'll see on a later slide how we fit all the robotic arms in the printer in that, and we're good there. As for the mass, we are provided with 70 kilograms of payload mass, and we're estimating 60 kilograms, including the printer, the filament, and the arms. Filament's going to be around 20 kilograms, which will be reloadable, and the printer is going to be the rest of that. As for the data, as we said before, we have a very good data rate of 100 gigabits per second and a 7-minute pass to effectively communicate with the ground station, and we'll be using Ethernet to communicate between the bus and the payload, which is very reliable and effective.
All right. One of our important operations is going to be leveling and location estimation, especially due to the special nature of our 3D printer. For location sensing, we're going to have a general movement precision of about 0.5 millimeters, and we'll be using some motor encoders and stereoscopic cameras to make sure that our depth and edge detection is up to par. For auto leveling, we'll have a 0.01 millimeter accuracy. We'll be using some laser sensors for that. And for the re-estimation of our state, we will make sure to do that after every single segment, just to make sure that we're on the right track and the print progresses well. And in terms of monitoring our print progress, we'll be using both a camera with computer vision to ensure that it doesn't fail and that we can continue printing as per the mission requirements.
All right, so next we're going to get into which filament we chose to go with, which was PEEK. So originally we went with Ultim. However, as you can see on our table here, it doesn't have a very good thermal range for the operating thermal range that we're using specifically, which is -40 to 71 degrees Celsius. So we chose conductive PEEK for its static dissipation qualities and the temperature range that it operates in.
Okay, so with our choice of PEEK, conductive PEEK to be specific as our chosen filament, we then looked at how we're going to feed this printer and keep that thermal management. So we're going to have a direct drive system. This differs from other systems like a Bowden tube. This helps aid in the heat dissipation and also requires a less powerful motor, along with our extrusion into the nozzle being within a near distance, so we have more control and less chance for clogs. We will include a large idler wheel in this system. This allows us for higher pressure and to have more force on our filament as we go through the nozzle to get those high flow rates. This would be less damaging to our filament and create less dust, which could hopefully prevent clogs and things like that. For our cooling path to the hot end, we went with the radiative hot end measure to kind of dissipate that heat. And this will help us maintain that 360 to 450 degrees Celsius temperature in our nozzle without allowing that heat to creep up to our motor and our direct drive system, so our filament doesn't melt prematurely and cause clogs. In the picture on the bottom right, you can see our whole entire payload SPAMM packed together with the filament 20 kilogram spool with 38 centimeter outer diameter and an 8 centimeter bore for like a roller. This also assumes 80% packing density. And you can also see the climbing arms and the robotic arm with the extruder head all packed in there. Slide.
All right, so next we're gonna move into the environmental feasibility portion. So this is gonna include outgassing, cold welding, thermal radiation, 3D printing and microgravity, and atmospheric oxygen. So firstly, for outgassing, NASA's requirements require us to have a total mass loss percentage of less than 1% and a collected volatile condensed materials percentage of less than 0.1%. So PEEK specifically has a percent TML of 0.14% and a percent CVCM of 0%, which obviously matches these requirements. For cold welding specifically, we're going to avoid metal on metal contact so that we can avoid this happening altogether. But in the cases that can't be done, we're also going to use lubricant on these surfaces. For thermal, our expected operating range is going to be -40 to 71 degrees Celsius in LEO and SunSync, and PEEK operates in -50 to 250 degrees Celsius. For radiation, so an overall mitigation technique is typically mission placement. However, polyethylene is also going to be a shielding technique for this, so we can avoid any further radiation. For 3D printing and microgravity, it's been proven possible by red wire and emission to the ISS, and regular 3D printers can also print upside down. So that's not really a worry for us. And then atmospheric oxygen, we're going to avoid use of polymers. However, in the case of PEEK specifically, we're going to use mitigation additives such as BTO or aluminum acetylacetate.
All right, so for our operations, we have a very unique payload that's going to be doing a lot of different things, and we identified 3 things that we need to have absolute confidence in for our mission. First off, station keeping. We want to make sure we have enough delta V to stay in orbit and that we can deorbit within 5 years. As you can see, we have 7,000 meters per second of delta V, and we will be using 50.5 meters per second per year for 5 years. So we're good on delta V. And we have an estimated orbit lifetime after end of life of 2.6, so we are going to be able to deorbit effectively. Next is attitude control. We were very concerned about the changing moment of inertia and changing center of mass as we're printing our parts, so that's going to change our disturbance torques and create a lot of uncertainty. This is why we're going to be using all that excess delta V to help desaturate reaction wheels and help with that attitude control. And we want to have extremely strong reaction wheels on this satellite. we're going to put a requirement of 0.005 Newton meters of torque on our reaction wheels. This is gives us a factor of safety of around 4.1 on the expected 0.0012 Newton meters of disturbance torques. And lastly, our ground station, we want to have effective communications. As we said before, our data rate of 1 gigabit per second is extremely effective, and we calculated signal to noise ratios. Typically, you want to see above 10 for these, and we have a 52 and 66 respectively for uplink and downlink, giving us very effective communications.
All right. So here's our failure modes and effects analysis diagram. So for this, our first risk will be the 3D printer itself failing. And then we have extended structural failure, climbing block grip failure, attitude disturbance, and climbing block motor failure. All right. So for our first risk of 3D printing failure, you can see we have a few causes and impacts for that. However, I'll be focusing on the actions we will be taking to mitigate this. So in addition to what we've already have on the slides, we will be testing and validating all of our prints with all the expected temperature variations of the orbit itself, as well as a few bonding sensors to ensure that the segments join properly and that the rail will not crack or deform while we are printing. For the specialized models, that will be a special software that we'll be using in order to make these prints due to the special nature of the printer itself, as well as the way it prints. And that should account for most of the errors.
Next, talking about our prototype. So we actually created a prototype, which is really cool. What we did was we started with a standard Core XY 3D printer, and we swapped out the print bed for our own Z movement mechanism. And so this movement mechanism is slightly different than what we intend to have on SPAMM, but we believe what we have on SPAMM is actually better than this design. The reason we went with this design was because it only required one motor, as SPAMM will, and while SPAMM will require 4 or more. And so this is just the Z movement mechanism from the actual design you see on screen. But how it works, how this design works is there is a gear that interfaces with our track, which just like SPAMM starts with an initial print segment. And this gear interfaces with the track and is able to move the track in the Z dimension. And then our printer was able to continue printing this structure and continue moving along the track. And so with this, we demonstrated movement along and continuous printing / extension of a 3D printed part, which is a big part of what SPAMM intends to do. And from this, some of our biggest lessons learned were the importance of accuracy, precision, and particularly vibration minimization and control. That was one of our biggest challenges, was dealing with vibration and minimization because it would significantly affect the print quality.
In terms of innovation and impact of our project, this will be the official first 3D printer operating in the vacuum of space. There was another one planned by NASA. However, that one did not officially launch. It had a similar capability. However, it worked in a different method. In terms of what we do, the printer mobility across the manufactured parts will obviously allow us to create megastructures. And this could also be a step towards von Neumann machines, otherwise known as self-replicating machines.
So next, we're going to talk about the biggest challenges and a potential tech gap. So firstly, orbital dynamics to maintain comms and power, which speaks for itself. Estimating realistic power draws for temperature maintenance. So this includes stuff like the hot end and keeping our printer going in eclipse. Filament selection, so that peak versus ultim decision. Our prototype, which you can see is now in the crowd. Our tech gap is going to include demonstration of 3D printer operation vacuum of space. This is a big tech gap simply because it's never been done before. For material science, our filament needs to be able to reduce the effect of atomic oxygen, which uses the additives previously mentioned. And then for reload, we need to have filament servicing in space.
Okay, so some innovative ideas that we covered when we were coming up with kind of how we would approach this overall ISAM design and what pillar we want to choose. We decided on growing gallium arsenide crystals as a possible idea where we could replenish photovoltaic cells, laser created structures,
You can also do some sort of manufacturing, and bioprinting using E. coli and silica to bond and create some sort of structure, and then molten metal manipulation using magnets.
Cool. So here's the abstract for our paper. Y'all know how it is. There's a PA process that our paper has to go through before it gets published. However, we expect that the paper should be ready in time for the SciTech conference submission on May 22nd.
And here's just a quick overview of our path to PDR. So we have a lot of actions that we wish to take. So more detailed computer architecture, getting detailed XSAT specifications and model, component selection, which will lead to our interface design, an eventual CAD model, and then from that, our final power estimates, our complete thermal analysis, and a detailed orbital simulation. And we expect this all to be completable in about 5 months.
All right, that was a lot of information, big fire hose. So if you take nothing else away from this, here's what I want you to know about our project. SPAMM has an extremely unique locomotive design that will allow us to print across manufactured parts and print indefinitely large structures. This is a huge way to bypass launch constraints, and it is going to boost us to the future of manufacturing in space. This is not just another gadget that does like one specific thing. It's a whole new method of manufacturing in space. And with new tech gaps and bridges in technology, hopefully printing in metal after this is demonstrated, these broad applications such as deployables, habitats, there's endless applications to this. And with our prototype proving feasibility, welcome to the future of manufacturing in space.
Okay, questions from the judges.
Hey, this is Lieutenant Chris there. I have a question, if that's okay.
Go ahead.
Okay. Yeah, so first of all, great presentation. I'll say that most of the applications that the DoD is looking at right now for in-space assembly is going to be in like geo orbits. I'm not saying that it's impossible to do it in like a sun synchronous or LEO orbit, but was there any consideration for what the satellite would have to, or what the payload would have to look like to perform at a geo range?
I can take this. Yeah, thank you for the question. So the question was, hey, what are the considerations for this operating in a geosynchronous orbit? And the answer to that is really what we were doing when designing the orbit for this was considering the FCC guidelines of deorbiting within 5 years of end of mission life and kind of trying to avoid creating more space debris. So we decided LEO orbit would be good for a test design. We could consider moving out to GEO for future orbits or for future missions. Honestly, we would have to consider how the data rate is changed on the uplink of the G code. But aside from that, just as long as we have continuous print capability, continuous sun time, I don't see any reason why we would have any issues with GEO. Just for this project, however, we were considering FCC deorbiting guidelines.
Hey guys, this is Greenfield from NASA Ames.
Go ahead.
Oh, sorry, is someone going? All right, I'm just gonna finish. I'm gonna finish my question really quick. I really like your guys' concept, and I think it really aligns well not only with the additive manufacturing of structures, but also on the assembly side. A lot of these concepts can be applied directly to how assembled structures can potentially look like. So I think following up in the future would be really cool. But one question I had was just about the working envelope of the robot arm and the mechanism. Do you guys have any more information related to that analysis?
So the current design, as you can see in the concept, is just a concept. And so that is totally dependent on what size robotic arm you're willing to use. And so, no, there has not been much analysis on the working envelope, but it would be somewhat radial from the robotic arm. But there's other things you can do to like increase the size of objects. So if you have uniquely shaped tracks, say going in like a toroidal kind of pattern around an object, then you might be able to work inside your envelope and effectively expand your envelope from just the robotic arm. Yeah, that's what I was trying to say. Yeah,
And
larger arm.
I think Scott had a question. I think that they'll wrap it up.
No, I was just going to ask, for the purposes of the experimental satellite, how long can you continuously print with the one reel that you got of filament on board? You're talking about a fairly long mission, but I don't think you've got enough.
Yes, do you want to just talk about how many volts per?
Yeah, so the question was, how can we continuously print with our filament? Over a year, we'll need 65 20-kilogram rolls to continuously print, and we'll use reloads continuously and docking so that we can continue printing. So that will minimize time and continue our operations in space.
Okay, thank you. That was outstanding. Audience, we can thank our speakers again. Thank you. Our next team is remote, and we will get started in 2 minutes. All right, I'll introduce the next team. It's Scramjet from Penn State University, and you guys can get started. And please, I think, yeah, if you have a camera, please turn it on. But if you don't, that's okay.
All right. Well, hi, everyone. We are Team Scramjet from Penn State. We are comprised of 6 fourth-year undergraduate students majoring in aerospace engineering. Our advisor is Dr. Sarah Lego, and our mentor is Dr. Ed Tate. Next slide, please. So my name is Maddie Canavy. I am the systems engineering lead, and I also oversee structures.
I'm Christian Bora. I am the command and data handling subsystem lead.
My name is Sophia Cotton, and I am the power subsystems lead. I'm Coral Lee, and I'm the communications lead and CAD lead.
I'm Ian McGrath. I'm responsible for the mission's propulsion system design and orbital mechanics.
And my name is Ryan Price, and I am the thermal subsystem lead. Next slide, please.
So when we were first looking into what we wanted the topic of our project to be, we looked a lot into satellites in orbit that are no longer functional and why they are no longer functional. And a common problem that we saw was the power system of these satellites. So there were a lot of situations where we saw the battery was out of charge, or it was dying or already dead. And from that, you're not able to fully power your satellite and continue on with your mission. And while there are missions that exist that repair a lot of physical deformities in satellites, there aren't any notable missions targeted specifically at the power system. So this is something that Scramjet hopes to fill by using induction charging to recharge a secondary cell battery in a target satellite. And we have the autonomous operations of rendezvousing with that target satellite, docking, and then of course the induction charging itself. This solution not only allows for a more sustainable choice by reducing the numbers of unnecessary space debris, but also allows for organizations to save money, time, and labor. Next slide, please. So in terms of our engineering milestones, the Scramjet team has been working together since late August of 2024. Initially, we selected our program manager and also defined some background research that we wanted to study as we continued on. From that research, we were able to define our top-level mission requirements, define a mission architecture, and also a functional decomposition breakdown. And we finished up our fall semester with a system requirements report. Starting in our spring semester, we began doing individual trade studies based on the subsystems that we were selected. We summarized those trade studies in a conceptual design report in mid-March, and since that report, we've been working on our path to PDR. Next slide, please.
This is the computer-aided design model of the scramjet payload. The isometric view highlights the subsystems within the payload with various arbitrary colors to highlight each subsystem's location. Equipped with adjustable layers, the payload's design is adaptable to further missions.
Pictured in the bottom left of the 3 view is the passive louver system. The louver blades will change angle due to the thermal radiation absorption and expansion of the bimetallic springs. The angles of the blades change based on the difference in thermal coefficients between the 2 fused metals within these bimetallic springs. A larger angle will correspond to a higher emissivity. Next slide, please.
Displayed is the concept of operations for the scramjet mission. First, the scramjet satellite rendezvous with the target satellite, approaching a safe distance for docking maneuvers. For our analysis, it is assumed that the scramjet satellite is launched in the same orbit as the target satellite. However, additional propellant for the scramjet satellite may be configured for orbital rendezvous maneuvers. Then in panel 2, attitude controls align the scramjet satellite with the docking face of the target satellite. Attitude maneuvers are completed by the attitude control system's 12 cold gas nitrogen thrusters.
In panel 3, a telescopic arm extends predominantly by a magnetic repulsion of the induction coil to the magnetic tip of the telescopic arm. The scramjet satellite is now primed to dock with the target satellite. In panel 4, once the telescopic arm is extended, a secure connection between the payload and target satellite are established. There is a probe on the end of the arm that is extended into the socket of the target satellite, as shown in the slide. The probe is secured by the target satellite by pushing a formed clamp around the probe. Once the target satellite is secured to the probe, the arm will retract back into the scramjet payload, bringing the scramjet and the target satellite's induction coils within 5 millimeters of each other to allow for efficient induction charging.
Once the connection is secured and the 2 faces are aligned, power will begin to flow to the scramjet induction coil from the payload's battery, as shown in panel 5. An inverter will be used to convert the DC power to AC because AC powered is required for the induction coil to function. The current flowing through the coil will create a magnetic field that flows through the target satellite's coil, generating a current in the target satellite's coil. A rectifier in the target satellite will be used to convert the AC power back to DC power, which will flow into the battery of the target satellite, repowering it. Next slide, please.
Next, the animation of the demonstrative scramjet mission procedure is shown. First, a Rocket Lab Electron rocket delivers the scramjet assembly and target satellite into a sun synchronous orbit. Then a scramjet satellite uses its attitude control system to make adjustments about its 3 spin axes to align with the target satellite.
Upon the alignment of the faces of each spacecraft, the doors located on the induction face of the spacecraft will open to allow the extension of the telescopic arm. Once extended, the spacecraft will maneuver, force the target spacecraft to initiate the docking procedure. Here, the target is made transparent to highlight the location of the induction coils. Next slide, please.
The thermal subsystem will integrate an external MLI blanket made of black Kapton laminate to reflect around 95 to 100% of the incoming solar radiation. An internal MLI blanket made of aluminized polyester film will insulate the propulsion tank and plumbing for extra redundancy. The passive louver ventilation system will be used as the main method of thermal dissipation, with a 7-blade set attached to a thermal radiator mounting system, having an effective emissivity of about 0.8. Next slide, please.
For the structure subsystem of the scramjet payload, we performed a material trade study and selected M60J, which is a high modulus carbon fiber, to be the primary material of the payload. This was verified using FEA through SolidWorks simulation. There are multiple shelves or levels within the payload itself that are also made of that carbon fiber material. They're supported by 4 carbon fiber rods that run through the 4 corners of each shelf. And these shelves allow for not only structural integrity within the internal of the payload, but also for securing components wherever we need them for the subsystem design. And of course, like we'd already described in our animation, there is the telescopic docking arm, which folds into itself through the center of the induction coil near the top of the payload. Next slide, please.
The power subsystem of the payload contains two components. One B28 275 28-volt lithium-ion modular battery with a capacity of 10.2 amp hours. This is used to store the energy from the bus and supply energy to the payload internals and induction coil. The other component is one 15-inch copper induction coil, which is used to charge the target satellite through induced charging. The power budget is also shown on this slide, and the power budget analysis resulted in a total of 309.75 watts of power being used between the payload and the bus out of the 444 watts of power allotted, with a 20% margin of 51.6 watts. Next slide, please.
The propulsion system of the scramjet payload was designed first by trade study of cold gas, monopropellant, and bipropellant engines. There were 35 total engines considered. The SVT-01 solenoid valve thruster was determined the best fit for the mission, which educated the analysis for the placement of 12 thrusters around the assembly. Concluding the propulsion design, the calculations of the gaseous nitrogen tank were performed. Next slide, please.
For the command and data handling subsystem, pictured on the left is a trace study comparing PC-104 to backplane for the integration of the subsystem, with backplane best suiting the needs of the mission, being a flexible configuration with high signal integrity and performance. Pictured on the graphic in the right shows a flow chart of communication between four main computers, that being a main computer, attitude orbit, power, and payload. The main will receive a code package from communications, which will then divvy out the commands to the relevant computers. Said computers will then carry out those commands and return their status to the main computer. The main computer will then store and compile the data to then be sent back to comms during an overhead pass. Next slide, please.
The bill of materials is shown along with the mass budget analysis. The mass budget analysis resulted in a total of 30.24 of the allotted 70 kilograms of mass being used by the payload, with a 20% margin of 5 kilograms. Next slide, please.
The scramjet payload will utilize the communication system of the bus with the following communication architecture. Using McMurdo Ground Station, located in Antarctica, to be conducive with a polar orbit, the ground station has a 10-meter antenna diameter at a 150 kilometer altitude and a transmitter power of 200 watts. The scramjet spacecraft will have pass opportunities with McMurdo approximately every 90 minutes, with an average download data rate of 1 megabyte per second, but a max of 1.92 megabits per second. An average upload data rate of 0.96 megabits per second, an uplink margin of 37.43 decibels, and a downlink margin of 40.7 decibels. The ground station and spacecraft will use an S-band frequency in 3 primary passes. During the first pass, both the scramjet and target spacecraft will downlink their orbital and power information to the respective ground stations. These 2 ground stations will send this information to the mission command station for processing and simulation verification. The second pass will be used to uplink autonomous orbital transfer, docking, and charging commands. The third pass will be used to verify successful mission completion. Any subsequent passes will be used to accommodate any error mitigation. Next slide, please.
Throughout the design process, many ideas were shared back and forth between the team. Pictured are the top 3 innovative concepts from our design process. Firstly, induction charging, being the primary method of our payload in using principles of induction to wirelessly charge a target satellite. Secondly, pictured is the telescopic arm and probe docking in order to safely dock and make contact with a target satellite. And lastly, although not used in the final design, magnetic docking, using a series of electromagnets to dock face-to-face with a target satellite. This design concept was to be the main docking method before the telescopic arm in tandem with the induction coil. Next slide, please.
A total of 5 risks have been identified over the course of the scramjet mission execution. First being docking operations. Docking operations require delta-V maneuvers that may change the orbit of the satellites, both scramjet and target. To mitigate the risk of atmospheric drag or other consequences of orbit change, the propellant loaded onto the scramjet payload will reserve ample thrust for a trajectory correction. In addition, with docking, failure of the telescopic arm's extension is present. The current strategy for extending the docking arm is to repel a magnet on the tip of the arm by the magnetic field induced by the induction coil. Extending the telescopic arm in this fashion offers confirmation that the induction coil is functioning and is an energy effective method. However, with so many sliding mechanisms, a risk of the arm being stuck may occur. To mitigate the risk of an incomplete arm extension, the scramjet assembly may induce a spin by the onboard cold gas thrusters, radially accelerating the probe arm outwards.
The third and fourth risk that was identified involved the power subsystem. So the third risk involves the induction coil on the far end of our payload, and that induction coil is responsible for creating that electromagnetic field that is going to essentially transfer the power from scramjet to the target satellite. With that electromagnetic field, there is the risk of affecting internals within the target satellite that aren't properly shielded. So to mitigate this risk, it's really going to come down to specifically in thoughtfully selecting our target satellite, ensuring we select a target satellite with high magnetic permeability in terms of their materials, and also with proper shielding in their components. The fourth risk is the distance between coils. We want to have our 2 coils as close as possible, around 5 millimeters for efficient inductive charging. But because of this, we recognize that charging all target satellites or all satellites in orbit is not always possible based on the geometry of not only the scramjet payload, but also the target satellite. To mitigate the strategy or mitigate this risk, we could look into using resonant inductive coupling. This is a similar concept to when you charge an electric car with a pad on the ground rather than plugging it in directly. You still have that large distance, yet you still have effective power transfer. So we could apply that concept directly to our payload and allow our payload to dock further away from a target satellite, yet still have a successful power transfer.
The final risk listed concerning the thermal subsystem is an eclipse or solar flare occurring, causing the temperature of the payload to fluctuate out of the operable temperature range for all of our equipment on board. And this range we found to be between -10 to 50 degrees Celsius. The mitigation strategy is to incorporate an active control backup system. This system will actively change the louver blades to the desired angle if onboard thermocouples find the payload fall out of our desired temperature range. Next slide, please.
As for the technological gaps which would enhance the performance of the scramjet mission if closed, the current propulsion system outfitted on the scramjet assembly is cold gas, which has a specific impulse of 70 seconds. If a compact, low-weight electric propulsion system would be available for scramjet integration, it would enable the scramjet mission to service multiple satellites. Electric propulsion systems offer specific impulses upwards of 1,000 seconds. However, it has proven challenging to the space industry to develop a small and reliable electric propulsion engine.
An overall battery would also improve the mission. Less energy would be lost during transfer and discharge for a more power-dense battery, and it would be able to store more energy for a more energy-dense battery, all while having smaller dimensions, leading to less space and mass being used for the battery. Having a higher discharge rate allows for quicker power delivery, therefore demanding less docking time. The battery trade study the scramjet team performed resulted in nickel-hydrogen batteries being the best fit for the mission. Though nickel-hydrogen batteries that can withstand space environments do exist, they are not readily available for use, so having them readily available would be extremely helpful to the mission.
While many standard docking suites are in place for large satellites like the International Space Station, this is not the case for small satellites. If a universal docking suite were to be in place for small satellites, Scramjet's mission could be marketed toward the wide range of global satellite makers, not just specifically designed to target satellites. Next slide, please. One of the most consistent issues faced was the development of a feasible docking solution. Multiple iterations included magnetic docking, as well as mechanically attaching the payload to the target satellite with a solid, non-retractable arm. The iteration process in itself showed that the progress of our research was healthy and constantly evolving to find the best possible solution. Taking a look at the next challenge, developing a propulsion system that was able to produce enough delta V for rendezvous with the target satellite was a large hurdle for project completion. The research process involved an in-depth trade study concerning different types of propellants and highlighted the importance of selection methods and thorough research. Finally, formulating the initial payload requirements for the scramjet mission was one of the first challenges the team encountered. Defining the purpose of the mission was hard initially because of the inflow of ideas from team members. This challenge highlighted the importance of team collaboration. Next slide, please.
The final report is 19 pages, contains 27 references, and has an abstract that is 200 words long. The team plans to submit to the upcoming AIAA SciTech Conference. Next slide, please.
The scramjet mission enriched the team with insights to use in future professional paths. Starting off, a thorough process is required to create a successful engineering design. A well-structured design process allowed for exploration of different solutions, careful analysis of potential risks, and the identification of any potential flaws before they became larger problems. Collaboration between subsystems was something that the team found to be extremely important as this semester progressed. Shared issues would arise that took multi-subsystem communication to appropriately fix. When our subsystems worked together seamlessly, it led to a more cohesive final product. And finally, extracting pertinent information research was critical to the mission, specifically condensing key points of research on individual subsystems to convey to other team members led to a more seamless final product. Next slide, please.
While a large portion of this project was designing our scramjet payload, we still had to look a lot into how we could integrate that payload successfully into the BCT Venus-class XSAT bus. In terms of structures, an aluminum alloy 6061 frame was selected. This was verified using the BCT Metal Procurement Standards brochure, as well as a launch load analysis via SolidWorks simulation.
The bus is assumed to contain one lithium-ion battery and use dual solar array panels. These components are verified through the information provided in Blue Canyon Technologies' bus datasheet and the constraints given in the Cosmic Capstone's request for proposal.
MLI blankets, the same as those used on the payload, will be used on the bus. A trade study like that of the payload was conducted for the bus and found deployable radiators to be most effective. This was verified using emissivity calculations, specifically Stefan-Boltzmann law, as well as heritage systems such as the D-cubed model. Given the BCT XSAT Venus-class bus datasheet states the bus is readily able to integrate chemical and electrical propulsion options, the small cold gas thrusters proposed by scramjet are assumed to be integrated onto the host spacecraft without issue.
With the CDH capabilities of the bus unknown, both the payload and the bus will be operating on the same CDH subsystem, as the simplicity of the mission commands allows for this. Verification was done through analysis on backplane integration, as well as component configuration based on our mission requirements.
The communication system will use a store and forward communications architecture on the S-band frequency. The information of this subsystem was verified using link budget analysis. Next slide, please.
While a lot has been done to successfully progress the scramjet mission design, there still is work to be done if the team wants to increase the mission's technology readiness level. For structures, additional FEA analysis is necessary with a more detailed CAD model featuring all internals. For the bus itself, I'd love to research more into the torques that are going to be expected on the solar arrays once in orbit.
For the payload, improving coil efficiency would ensure less docking time due to quicker power transfer and ensure that less heat and energy are lost during power transfer. So testing that with physical components to verify energy is efficiently being transferred between the internal components and throughout the payload would be crucial. For the bus, the information provided on the bus by BCT was vague, so we would also love to confirm the details of what specific dual solar array panels and batteries are used in the bus.
For the thermal subsystem, the next step for both the payload and the bus would be to use CAD software for thermal analysis. This would act as a secondary verification for the existing systems in place.
With the scramjet payload's propulsion system determined, an attitude determination and control system, or ADCS, is left to be designed to orient the vehicle for docking, spinning, and trajectory correction maneuvers. In addition, a docking simulation is to take place such that the ADCS is able to autonomously maneuver the telescopic docking suite with the target satellite. The same design procedures are to take place with the bus.
And for the CDH subsystem, for future work for both the payload and the bus, analysis will be done through OpenC3 Cosmos to better get an exact configuration for our subsystem. Next slide, please. So in conclusion, the scramjet mission tackles prolonging the lifespan of a target satellite through power resupply via innovations with the close contact induction charger and the telescopic arm and probe docking system. The importance of power resupply cannot be overstated for the future ISAM missions. The ability to increase servicing to decommissioned satellites and reduce overall space debris while saving money, resources, and labor can open doors to prolonging in-progress missions already overhead within the field of ISAM.
Next slide, please.
There's just been an earthquake in San Diego, but I think we're okay.
Oh my goodness. I hope everyone's okay.
Probably won't feel it. 5.8 though, so.
Oh,
who knows?
wow. Oh my goodness.
You have groundbreaking technology.
With that segue, we'll open it up to questions for the judges. I appreciate the earthquake waiting till the end of their.
It was good timing.
I think Aiden wins with that last comment. Hey, one question. I do have a question as a judge, Dr. Greer. You showed your orbital profile as using McMurdo in a sun synchronous orbit, but early on you talked about being launched into the orbit of your target in an operational context, not just your demonstration, right? So if you had to deal with eclipse in a lower inclination orbit, how would that change your design, if at all?
Right. Okay. Sorry, we are in the same room, so we're flipping back and forth between muting and unmuting. So your question concerns whether we are launching for our demonstrative mission on the same orbit or targeting a pre-existing already in orbit satellite.
Well, you showed analysis or at least a design concept for a sun synchronous orbit, which is around 90 degrees. But your ideal would be to launch into the orbit of a target satellite that needs help, which may or may not be in a sun synchronous orbit. How does that change the design of your payload?
Absolutely. So this is a multi-headed question, and I have multiple answers for you. So our entire analysis delved into, and in fact, you can flip to it'll be slide 32. And that's our orbital analysis and our extra slides. And so this was the basis for how our mission was going to operate. It was a 550 or 500 kilometer altitude sun synchronous orbit, and that was per Electron's launch. This is not the slide. It is after our questions. Yes. The title is Orbital Analysis. Excellent, thank you. And so this was done in ANSYS SDK, and given the data acquired from this analysis, we told Ryan, our thermal lead, okay, we have this amount of sun flux to deal with. This educated our
sun sensor and ADCS thruster placements, etc. And so if you were to launch into a mission or a target satellite that is not in a sun synchronous orbit, yes, we would certainly have considerations in half of the solar flux to be expected. In addition to probably more propellant being loaded onto the payload to rendezvous with that spacecraft, because Electron's launch site is in the Mahia Peninsula in New Zealand. That's not on the slide, I'm sorry, but that's at a lower altitude of planet Earth, and so we can launch into a sun synchronous orbit a lot easier. And so if you were to scroll up, please, to the potential target mission, the Landsat Next slide. And this was a great example of a scramjet mission target satellite. A few more. Yeah, it's slide 25. It's just below the question slide. Excellent, thank you. And so, not to disregard your question, because it's a good question, we have to consider other orbits to place our mission in, but this is a great example of what a scramjet mission could be utilized for. So the Landsat missions have historically been placed in a sun synchronous orbit. It's a great orbit to get the most coverage of Earth's surface. And their purpose is, of course, Earth observation and monitoring. It is going to be launched in 2031, and it is in the concept and technology development phase, meaning we could contact NASA and say, hey, we have this great idea. We can service your satellites, service your mission, and recharge your 3 observatories in this sun synchronous orbit if you were to include our target satellite docking suite, the socket, if you will, that you saw in our concept of operations. And the lifespan is 5 years. We could extend the mission lifespan to, say, 6 or 7, given a scramjet mission is bouncing back and forth in this sun synchronous orbit to these 3 observatories and refueling by induction.
It went a little long, but we can take one more question from the judges. Okay, so we're gonna go on a 15-minute break here. But what we would like to do for those of you in El Segundo is right at the start of this break, we'd like to get a group photo in front of the screen. Yeah, okay. So we'll break here, we'll get in front of the screen, and our photographer in the back will direct us. Everyone else, we'll see you back here at 10:30. Thank you very much.
Yeah, back row, no, no blinking, hold miles, ready, 1, 2, 3. All right, thank you. And he's somewhere. Okay, you too. One of the mammoths next weekend. That's great. Right after, right when we go. You should have got the message before we were there.
Yeah, one of my teams in Houston right now. But yeah, walk away.
We're trying to stand this one. We're coming in arrival.
Oh, we got started. No, that was like, I like forgot that we were waiting for you. When I was talking, I was like, man, oh shit, I saw you like coming to this first time.
We're bringing this.
My boss is, I met her just briefly, 4 weeks ago. Well, the distance markers are kind of like a logger thing you're gonna yeah, just refresh. Yeah. What else next to you?
Everyone come back in the room. We're gonna start.
I was walking around.
Nothing.
Yeah. No, we're on time.
We're gonna get started at 10:35 sharp, which is just a 5-minute delay, just to allow everyone to get back to their seats here.
I think we have to ask them to click it for us. Oh, no? Oh, okay. Mess with it, make sure we know which way is the right way.
Laser pointer's so faint.
It is class 2.
We're real class 2 tonight.
That's backwards. I'm just gonna make sure this is forwards. Nope.
Maybe it's stuff.
It might
But they
not
were
be your
pointing it like
control
at this TV.
Yeah. I just want to make sure we're hitting the right way.
Why?
Because Shaw's computer's dead, or we get brownie points. Someone's got their charger. They could go in.
What type?
Plug them up. I think it just needs USB 40 watts. We wanted to get notes for us, and they can't get notes because they can't get help. Should have been very hard. You have a very good morning. First. Did you click it?
Nothing happened when I clicked any of the buttons. I didn't click the bottom one.
You should probably keep everyone like to do line order type thing.
Yeah.
So you're after me, so.
Yeah, I think the Zoom is still paused as well.
Well, we're going to 35 exactly.
Oh, okay, we're going to 30.
It's a 35.
I'm hard, that's it.
Should be okay now. Yeah. It's the time. What if I said? First one. That's what you better first. That's for sure. Yeah. They're pretty good. Very professional. They're on top of it. Far opposite.
You want to be over here?
I'm just gonna put this down so I can just open it.
Should be open by now.
Nice talking about.
No, the notes.
Yeah, so I can just like quick glance. I'm literally gonna just lay these out like this when I put them on.
Kevin, yeah, I think literally
The breast.
just about is.
I ain't ready though.
I
I know that's the scary part. I'm just like freaking out and just doing nothing.
Like, just imagine like it's the first Spider-Man movie.
The
And
first
this is
Spider-Man
Macho Man, Randy Savage, and you're Spider.
Okay. It's just that is a big.
Yeah.
Just a bunch of others.
Oh,
How many are down?
Ben.
Yeah,
That's always a doctor.
No, he's no. It's master's. He said he did like doctoral work at USC, but he never done anything. Like he did classes at USC, like for like post, but he never officially done it.
I know, that's why I had to
Look on his LinkedIn, it says like.
Yeah.
Huh? My phone is on.
They want me to throw my beats, bro. They're in my backpack, but I'm just like, I can't do it. Just those four products.
Starting in 2 minutes. If you're in El Segundo, please return to your seat, or if you want to stay in the break room, make sure you're not chatting. So it's quiet in here. Thank you. Okay, we'll start in just a few seconds here. Our next team up is CSUN ISAM, and they're actually a predecessor team did the prior challenge last year, and they've carried on the name. It looks like they carried on a lot of the traditions, including the matching polos. Professor Dr. Shaw here is their advisor again, and Alozer Plotke, who many of us know at Aerospace, who's very active in the ISAM community. He is a proud CSUN alum, and he is their mentor. So with that, I'm going to turn it over to you guys. Go ahead.
Thank you. My name is Donovan. I'm one of our systems engineers, and joining me is our PM, Lewis, and then our 3 sub-team leads, Alberto, Samuel, and Andrew. And this is our work breakdown structure. You can see the PM at the top, our key stakeholders, Dr. Christoph Schall and Elza Plotke, systems engineers and team leads under that highlighted in pink. Going to our ConOps, it starts just like any other space mission. We're going to get inserted into our initial orbit, which is going to be in LEO, low Earth orbit, and polar. Once we get to our target orbit, we're going to begin phase 1, which is going to be detection. As we are doing space debris remediation, we're going to detect debris and then rendezvous with it. Going into phase 2, analyze it outside of our payload. Phase 3, capture it and bring it into our payload. Phase 4, store it and analysis. And then you have a downlink of the data that we've collected of our debris, and then repeat that process again, either 12 times or until a year elapses, and that's going to be our end of mission. And then we'll either unload the debris we've captured onto a recycling facility in LEO or wherever NASA is going to be putting their recycling facility, or we will deorbit and splash down or burn up in the atmosphere. So the impact, we're going after lethal non-trackables, or LNTs, which is debris that is between 1 and 10 centimeters in length. You can't track it from Earth. And they're all going to be in a specific debris cloud, which has the same body of origin. So it maintains the same altitude and roughly the same kinetic energy. By removing and analyzing this debris, we'll make it a lot safer for future ISAM endeavors and cost effective, because there'll be less maneuvering around the debris, and we'll know where it is based off of our detection system and data. As you can see by the pink line in that first graph brought to us by Maclay in 2020, they did a study on fragmented debris, and they found roughly 9,000 to 10,000 pieces of debris, and that's trackable. And there are orders of magnitude more LNTs than there are trackable debris. So it's a major problem because it can cause catastrophic damage to all the systems and in LEO that are up there now. We're going to detect, localize, or locate that debris, find where it is, where it's going, capture it and analyze it, get a 3D model of the debris itself, and remove it from low Earth orbit, and then either recycle it or just get it out and burn up. We're going to do that with a system of our detection system is going to be with radar and infrared cameras, and we'll capture it with a mechanical arm and store it, and then also analyze it with a few devices that we'll go into in the next slides. Our current project status, according to NASA System Engineering Handbook, we've completed pre-phase A, phase A, and we're moving into phase B. The payload that we decided to use was the dual solar array given to us by the Venus X-class bus. And we chose the dual solar array, even though it gave us a less volume. We needed that extra power so that we can increase our detection range and accuracy. Since we're operating in low Earth orbit, we have our temperature, our thermal cycle listed, as well as the pressures, radiations that we're going to be exposed to, and our atomic oxygen levels. Going into our rough power budget, you can see at the bottom row, it's our efficiency and losses. So we're accounting for a 10% just in exchange from our batteries to all of our devices and give us a cushion. In phase one, we have detection, which is going to be taking up all of our power for the moment, going for long range, moving into close range, which is where phase two comes in. But we're going to analyze the debris outside the payload, but we still need to locate it. That's why we're going to keep some power into detection. In phase three, we're going to actually capture that debris. And moving into phase four, we're going to analyze it again and then store it. And you can see that we have left some power for heating just to maintain operating temperatures. Moving into the mass and volume budget, we're going to be using roughly the same material across all of the subsystems. So it's going to be proportionally the same. And we're also accounting for a 5% efficiency. So the allowable mass is as shown. The data management, we're going to need to downlink just a few things. The two-line element data, or TLE, which gives us position, things like inclination, altitude of the debris that we're tracking. The volume of that debris that we've captured and analyzed, as well as the material results from our analysis. It'd be nice if we could also downlink the images from our photogrammetry, which is what's going to give us a 3D model, or the 3D model itself, or spectroscopy, which is what's going to give us that material data after it's interpolated. The requirements are we're just going to need some uplink data of TLE of other debris clouds that we're not going to be in for maneuvering and avoiding collisions. Ground stations are going to receive data just so that they know each one of our subsystems are working properly. And we will just need a little bit of onboard storage so that we can hold that data while we're in between downlink stations. And we will not need any real-time downlinking. Going into our systems engineering milestones, which is outlined by the NASA System Engineering Handbook, you can see that we've completed pre-phase A, which has our preliminary research and our development of ConOps, or concept of operations, and moving into our trade studies, which goes into phase A, and then our system requirement review, culminating with our conceptual design review. And moving into phase B, we have our prototyping and prototype demonstration. And on our full mission plan, you can see that we're roughly entering year 2, where we're formulating our PDR. Then it goes all the way until year 6, which is going to be phase E, the active phase, where our payload is going to be doing the mission itself, and then close out at the end of year 6, start of year 7 with the burn up or offloading that debris onto a recycling facility. Here you can see the conceptual design of our payload. We color coordinated it just so you can make it out a little bit better. That red part is going to be our capture assembly. We have our capturing mechanism at the end of a mechanical arm, which is that tube structure in the front. And then also a secondary arm to manipulate the debris once it's inside of our payload. And underneath that secondary arm is our storage for categorizing. Moving down, all the pink is going to be our detection system. The thing right in the middle is our radar horn, which is what we're going to use for long range. And you can see in opposing corners is going to be the IR cameras, so we can localize that specific piece of debris. And then our analysis subsystem, the two eyeball-looking things at the top are going to be our laser-induced breakdown spectroscopy devices, which is going to give us that material data. And in the far back left corner, if you can see that, is going to be our photogrammetry system, which is going to take a series of pictures, which will give us a 3D model of our debris. You can also see we've allocated some space in that back right side for our computing power and data storage. Moving on to our detection system, I'll hand it off to Andrew.
All right, and here we have the trade studies for the long-range detection subsystem. First off, we have the LiDAR system, specifically a 360-degree LiDAR system. This was ultimately not chosen due to the fact that no commercial systems fit the needed range parameters due to mainly laser divergence. Next, we have the phased array radar. This is ideally the perfect system for this detection subsystem. However, it ultimately was not chosen due to the very complex design and manufacturing that would need to take place. Then we have the cast grain radar system, which you could see in yellow has the primary parabolic reflector. And then in the center there is going to be the feed antenna. And there could be multiple variations of the feed antenna for different performance. This system has a very high gain and it has mechanical steering, but due to the very high weight and volume constraints, we did not go with this one. Finally, we have the horn emitter. This one has slightly suffers in performance compared to the cast grain antenna and the phased array radar. However, it does best with power, volume, and weight. So this is ultimately why we chose it. Here we have the trade studies for the short range detection subsystem. First off, we have visible light cameras. These ultimately were not chosen due to variations in the potential amount of light available due to potential variations in operating orbit, which could limit the amount of light used for detection. Then we have single point laser rangefinders. These were ultimately decided not to be used due to the fact that this would be a single point detection system, whereas the other two cameras would be a field of view system, which would be much more efficient for what we need. So ultimately, we went with the infrared camera system, specifically a stereo camera system where there would be two infrared cameras. Infrared cameras are widely used in space and well known. And on top of that, we could be detecting heat instead of actual visible light, which would give infrared cameras an edge. And so here we have the partial animation of the detection subsystem. Specifically, we would arrive at our designated orbit. The mechanical arm for the antenna would unfold. The radar system would initialize and search for the LNTs at the maximum possible range. The radar system would acquire an initial object, and the payload would then head towards it. The radar system would routinely update relative position and velocity to this object. At a specific designated range, the infrared cameras would then take over, and they would observe and obtain a relative geometry profile of the object to see if operation would continue with this object. And if so, the handoff to the analysis team for laser-induced breakdown spectroscopy as an analysis method would begin. And now I will hand it off to the analysis team lead, Daniel.
Hello. So the analysis subsystem identified methods to determine material composition as well as geometry. Beginning with trade studies of methods we determined to look at material composition, we looked at primary candidates including laser ultrasound, eddy currents, and laser-induced breakdown spectroscopy, or LIBS for short. The primary selection criteria were SWaP-C, and testing ranges. We were ideally looking to do testing outside of the payload, so we were looking for range in the meters. So eddy currents was eliminated due to its short range. It needs near contact range in potentially millimeters. Laser ultrasound had an acceptable range. However, due to SWaP-C criteria, it was incredibly weight intensive, exceeding our budget for our part of the payload. And there were also technical difficulties with getting it to operate in space. It's a very difficult method. Thus, we moved forward to laser-induced breakdown spectroscopy as it fulfilled our SWaP-C category, and the testing range was variable and was sufficient. From there, we move on to the different trade studies of our geometry analyzing methods. We identified 3D laser scanning and photogrammetry as potential candidates. For this, again, we resorted to SWaP-C. 3D laser scanning generally weighed more, cost more, and required more power. So photogrammetry was elected as being superior. And additionally, 3D laser scanning required more computing powers to run the softwares. So we move forward with photogrammetry for that. Here you can see our aiming system for our LIBS. The item on the left is going to be a focusing lens that the laser is fired through that will pulse and create a plasma plume. And on the item on the right leads into our spectrometer with a fiber optic cable. And the spectrometer will analyze the plasma plume and determine the material composition. After the piece is captured, we will conduct photogrammetry. We have a staging area. The piece will be inside of our secondary robotic arm, and it will rotate at 18-degree increments, and a variety of photos will be taken. And these photos will be uploaded into softwares such as MeshLab. And from there, point clouds will be generated. And then from there, 3D models will be generated. And from the 3D models, volume calculations, geometric dimensioning will be done. So from here, I'm going to pass it off to our capture team lead, Alberto.
So beginning with the trade studies for the capture mechanism, the first one on the left would be the two-layer adhesive panel, which is a combination of capture and storage that would use various adhesives to actually embed the debris that's coming towards it. However, due to various radiations and space dust, that it could be we have feared that the capture mechanism could be rendered obsolete before actually completing the space mission. So we moved on to the capture mechanism on the right that's called the bullet catcher, which is defined from an actual gun range bullet catcher that deflects the debris downward, and using it for this specific configuration, we would close the opening and use a confining plate to stop all potential rotation and movement from the debris, and there would be an opening on the back of the bullet capture that would allow us to extract the piece of debris once motion has been confirmed to stop. The issue that we ran into with the bullet catcher is that due to its large mass and volume that it would acquire to actually be operational and relatively ease of use for us, was above our constraints given to us. So we moved on from that into the capture mechanism known as the cup, which is attached to a robotic arm consisting of a shell and two end effectors that we will get into more detail later about how it specifically operates. And moving on to the storage trade studies for capture, we have two ideas. One was the dual sliding boxes, the other one was the cabinet. The dual sliding boxes was placed outside of the payload, but due to concerns of having it be a potential risk for us every time it opens and closes, we had decided to move forward with the cabinet, which is derived off of a filing cabinet, which allows us to more categorically compartmentalize the debris based on different materials. And the reason we have storage was stated earlier by our system engineers. We would prefer to actually recycle in the future the debris that we capture. And moving forward to our animation of the main robotic arm. First, we have the unfurling of the robotic arm, in which the cup and the arm would align itself with the expected trajectory of the debris based off the data given to us by the detection subsystem. From there, the cup's first end effector would rotate open, allowing the debris to cross into the shell, and then rotate close once it senses that it is in the shell. Then the secondary end effector on the back with the lead screw would confine the debris, and finally the shell will retract to allow extraction of the debris with our use of a secondary arm. And then from here, I would like to pass it off to our project manager, Lewis.
Thank you. So onto our most innovative concepts. The cup allows us to constrain the tumbling and the rotation of the debris. And it also allows us to have a precise location of where that debris is in our payload. For laser ultrasound, that hasn't been displayed in space, and it also determines the material properties, which is something we are looking for. The two-layer adhesive panel, that is an attractive option because that allows us to capture multiple pieces of debris, and it also acts as a storage device. There we go. All right, some important technology gaps for the phased array radar. The amount of elements needed and the complexity for manufacturing proved to be just a little bit out of our scope. The manipulator arm, the precision needed to control some of these 1 to 5 centimeter pieces proved to be very difficult. The sensor for the capturing mechanism, that is a critical component because that detects when the piece of debris is in the cup, and it also it's vulnerable to damage because the debris is also in the cup. Some of the biggest challenges was determining RPO and orbital mechanics. That is a fundamental part of mission planning. And because we have such limited fuel to use, that allows us to calculate efficient successive rendezvous operations. For the phased array radar, it was very power intensive, and it was difficult to integrate into our overall design. So optimizing some of those would prove to be pretty difficult. Also, the reliability of the capture mechanism, since the high kinetic energy of some of these debris could damage the cup, testing would have to be done to see if it can withstand some of these collisions. So we have 3 risk categories, and we decided to highlight 4 of them. The first risk is the complete loss of the detection system. And a mitigation strategy that we can implement is provide redundancy for the key detection components. Another risk we have is the payload operating outside of our prescribed temperature zone or range. This would mean that we need a robust thermal management system that would have to be implemented as well. The debris damaging the capturing device, that would, we can mitigate that by impact risks, running tests, and implementing debris avoidance strategies. And lastly, the project fails to meet timeline and budget constraints, so clear goals need to be established throughout the project. In the path to the PDR, designing docking and connection systems to the host bus would be probably the first step. We would then finalize the specific components for each system, as well as the accessories needed to attach it to the payload subframe. Finalizing of the subsystem circuit design, as well as implementing data budget and network protocols. Once we do geometric dimensioning and tolerancing, we can conduct finite element analysis for each of the subsystems and the payload itself. And then finally, we would determine thermal coatings for the payload to protect it against thermal cycling. For detection, we decided to demonstrate a piece of debris going towards our payload. Using an AR camera, we can develop a surface temperature profile. For libs, we have motion tracking and targeting for the libs laser that will be used to characterize a piece of debris. For photogrammetry, we developed a point cloud, seen right here to the right, using a camera and a motor. And lastly, we have the capture cup. The capture cup here detects the piece of debris, it closes, and it retracts, which allows the secondary arm to go in and grab the piece of debris and move it to the next stage in the process. And then next to that, we have the storage system, which opens and closes once it detects a piece of debris in it. As for the paper, you will find a lot of this info that goes a lot more into detail, such as the problem definition, the scope, general requirements, and project innovations. And lastly, just to summarize, we're going after, or we're detecting LNTs, lethal non-trackables. That's in the 1 to 5 centimeter range. We're going to capture it using the containment cup. We're going to analyze the debris for categorization purposes to expand the categorization catalog that various agencies are working together. We are going to store the material with the intention of future recycling missions should the technology be proven to be feasible. Some of the lessons learned, order parts for the prototype. Delays are inevitable, such as shipping and lead time. Environmental gaps, no vacuum or thermal testing yet. So we need to replicate space conditions down here on Earth to test some of these components. For future improvements, we can add a secondary detection system that would provide redundancy, and it would expand our range that we can look into space. We would also test in thermal vacuum chambers to assess the real world viability. And although each subsystem can be implemented and operated independently, together we can automate the entire process, and that would provide rapid multi-capture capability. I'll open the floor to questions.
if I may, I may have missed it, but what kind of debris are you after? What is worth recycling on the scale of 1 to 5 centimeters?
Most of it's going to be metal, which I believe was titanium, aluminum, and we have a separate category, which is other. So that can be, you know, any piece of plastic or carbon, and that goes in that would be a separate category that probably wouldn't be recycled, and that would be just part of the deorbit plan.
And do you have a step where you make a selection whether you capture a debris? So with the libs, you're gonna know what it is.
So just because lethal non-trackables are a concern, we will be capturing every lethal non-trackable we target and RPO with. So we are categorizing them for future recycling and scaling. We're hoping in the future we can scale the satellite or scale the project to be able to store more pieces, or these technologies can be utilized in payloads targeting larger pieces as well. But with the cost of sending anything into orbit, every single piece of material counts. So that's why we decided even for these small pieces, it's valuable. And again, targeting every single lethal non-trackable and capturing it is for the safety of all satellites. So we'll capture everything, whether it meets our criteria for recyclable material or not.
Thank you.
I have a question. What's the max velocity you're designing to in terms of capture? The object coming at the cup.
Relative velocity.
Yeah, relative velocity. Yeah. Thank you.
We initially started our calculations with the idea of having to do 5 meters a second or less. However, due to various factors that we still have to consider, such as the speed of the robotic arm, the adhesive used for the end effectors, that could vary in the future to either be less or more. But as of right now, relatively, we started with the idea of 5 centimeters and are starting to work our way down to see what is viable.
Okay, any other questions from the judges?
Yeah, I have a question. Were there any considerations on back contamination to Earth or wherever you're sending these recycled materials? And second question is, what if there are some LNTs that you don't want to necessarily capture? Maybe they damage the system. So I'm just wondering, beyond capturing whatever's tracked as an LNT and assuming it's safe, what considerations have been given?
So one of the things was unfortunately not pictured due to time constraints was the a concept of operations for multiple subteams, and there were requirements on how fast debris was going. So if it did exceed a relative velocity of 5 meters per second, there would be a chain of operations to disinclude that debris and to move on to a next piece of debris if it looked like it could potentially damage any part of the payload.
Then I think there was a part of that question about back contamination.
Right. Yeah.
So yeah, for the portion of recycling, that was based on NASA and ESA both having plans to have recycling facilities outside of Earth. I think ESA was going to put one at Leo, and then NASA said they would have one either on or orbiting the moon.
Okay.
So whether or not, that's actually in place would determine whether or not we'd just have a splashdown or burn up or offload that.
Okay. So that whole part's there. Okay, thanks.
Okay, do any of the other judges have questions?
I may have missed it. Was there a data handling chart in the package?
Oh, okay. So there was a slide on the data handling. Unfortunately, we still do need to go through as part of the path to the PDR to determine, I guess, the total amount of bandwidth that we'd need up and down in order to transmit the required downlink data. But we did want to highlight that the required downlink data would be significantly less than the desired downlink data. So this project could get by with a lot less data capabilities than what it could have as a potential highlight.
Great, thank you.
Okay, I want to thank our speakers and if the rest of your team can join you on stage.
Professor, do you want to pass around the code? We can pass it around.
I mean,
Just put it on the table.
Yeah, just so people can see.
Okay, excuse me. The cup.
That's great. Thanks, I tried.
I mean, we brought you up here for expertise. I mean, you did exactly what we asked you to do.
Total, I believe this is 1.4.
Where's it getting bigger?
I thought here it's like 19, no? 20? Oh, wait, 19. He doesn't want to, he doesn't like us.
Yes.
Yes.
Again, back row, you jump under the toes.
Great job.
And once they get down, the next team is going to make their way on stage. I believe they may be a mix of in-person and remote. But yeah, next up is Weldinator from Cal State Los Angeles. So this is kind of our Cal State segment. We had Cal State Northridge, now Cal State Los Angeles, and next is San Diego State. But right now it's Weldinator. Once you're up there, guys, and the screen's being shared, you can get started. Just another minute or two here. Okay, you guys can get started. I'll give you the 2 minutes back on the back end.
Alrighty, guys. So we're the Weldinator from Cal State LA. My name is Florencio Dominguez.
My name is Indio Shaw.
And my name is Francisco Prieto.
I'm Adrian Alvarez.
RJ Denley.
Okay, so first things first, we need to identify the problem, right? So not really a problem, but more of a solution. There is a need for infrastructure in space. This will lead us to longer missions rather than short parabolic flights. Our proposal is that we can maintain and repair spacecraft for longer durations of flights. The capability that we're proposing is that we weld 1/4-inch wire for infrastructure purposes. It is important to note that we're we're assuming that the wire is already in space for us to weld. How does this solve the problem? It helps fortify infrastructure in space without the need of pre-built systems here on Earth to be sent into space. The ability to repair damages on current systems in space, and it also reduces costs to launch infrastructure into space that are already built here on Earth. The current status of this project, while the welding in space is very promising because there is successful testing of Think Orbital or ESA using electric beam welding already being used in space. And this will help us help construct habitats, maintain spacecraft, and assemble infrastructure.
And as mentioned, the impact of why this is beneficial, well, it's because we're going to be able to construct structures in space in which we can later put more systems on, and this will help further space exploration. This can also fortify already existing structures in space. So what we're referring to is our cohort team at Cal State LA is doing a bending of a 1/4-inch steel, stainless steel. And so what we are proposing is to be able to weld that, to fortify that, to create stronger structures in space. This welder could have the ability to repair and maintain spacecraft. This is just a capability that a robot could potentially be used for.
Our system is pretty feasible. We chose, well, all the elements of our system. We conducted trade studies, and one of the categories in that trade study was the technology readiness level of each. And using all those, we chose all the elements that had pretty high TRL levels. And some of the technical challenges were the energy constraints, thermal management, miniaturization, and autonomy. And some mitigation techniques that we used was power optimization, thermal control systems, and sensor redundancy.
RJ, you're muted.
Sorry about that. With our welder or auto welder in space, the core innovation lies with integrating robotic automation with welding, eliminating the need for multiple tool sets or excessive material pre-launch and post-launch. And instead of sending pre-built structures to space, our welder allows us to maintain and repair in space versus sending separate materials. Additionally, it's designed to work with other technologies like robotic arms or rovers, making it modular and scalable for future projects if needed. Next slide.
And when it comes to performing said action, well, 316 stainless steel, it's good enough to be working in space, just kind of like as is. But constraints that we have for our actual payload design is that we have the payload volume limit of like 17 inches by 6.4 by 27 inches. And this is the constraints that we kind of have to make sure everything could fit within to be attached to the satellite. And then the energy storage thing, which is going to be a major factor for us, is going to be 10.2 amp hours. And then similarly with mass being a very important factor. And things that we had to take into consideration while we were doing or planning this out and doing the research was that the environmental factors were going to play a very huge role. And we had to take into account the microgravity, vacuum, the temperature range for our components, as well as the material that we're welding, if it's facing the sun, facing away the sun, and then just some weight properties as well as getting the metal to its melting point and allowing it to be a good weld that will secure the beam or wires. Sorry. Next slide.
All right, so I was in charge of choosing the sensors in which we're going to be using. So I chose this SmartRay Eco X100, which is going to be a vision sensor. And so what its purpose is going to be to inspect the weld. SmartRay has a Josie software that it's able to inline inspect the weld. And so these are some of the specs for this sensor. Some of the key ones that I looked at was going to be the weight. weight, power. For this specific sensor, I believe the average was about 8, and max was 10. The temperature range for this sensor, since it's been used in the automotive industry, it's going to be -20 to 70, and we're going to be mitigating this to increase the range of the temperature with space materials, so that's space ready. And so the way it's going to work is going to use a laser triangulation to create to look at where the weld is going to be welded, and then it's going to be able to create a 3D model of that and inspect the weld and be able to determine if it's a good or not weld. Yeah. Going over to the LiDAR sensor we're going to be using. It's called a LiveVox Mid 40. And so what the purpose of this sensor is going to be is to be able to map out where these wires are located so that it could detect where the clamp should clamp onto. And so again, these are some of the specs for this sensor. And essentially what it's going to do is going to look for that reflecting surface. And since we're looking at stainless steel, it's able to detect that for us and be able to process that distance, again, to be able to communicate with our systems and be able to tell the clamps where to clamp onto.
So my teammate did mention clamps, and the purpose for these clamps is, okay, we're in open space and we have wire. How are we going to weld the wire? So a proposal to this is we have these clamps to grab onto the wire and to stabilize the whole system as a whole. The mass for each clamp will be 6 kilograms each, a total of 12, because there will be 2 clamps that will grab onto the wire. The power consumption for these clamps will be about 1 to 5 watts. They will be driven by brushless DC motors, and they will be made of T6 6061 aluminum, which will withstand the harsh temperatures of space. The gears driving these clamps will be lubricated with a solid-based lubricant, Teflon, since we can't use liquid-based lubricants.
There were various movement mechanism ideas that we considered, and ultimately we came down to using a robotic arm. The robotic arm that we're using is the X-Link modular robotic arm system from Motive Space Systems. This arm is currently being used on the OSAM-2 mission by NASA, and the configuration we're going to have is 6 degrees of freedom. It'll weigh 22 kilograms. It will have 125 to 150 watts power consumption, and when fully extended, it will be 35.9 inches in height. And when it's compact, as you can see on the right figure, that's how it normally is going to be. And when it's compact like that, it can fit within the volume constraints that we're given. And how the robotic arm is going to work is mainly relying on the sensors. Once the sensors process the information, it'll relay the information to the arm, so that it can move the welder to the position to weld. And once there's no more like welding positions, it'll fold back up into the compact form.
So some risks that we do need to be aware of, for example, right now are environmental risks. There is a risk of solar radiation, which in effect can harm electrical components, which makes electric malfunctions. There's a degradation of materials that could be affected in play. Some mitigation for this is using multi-layer insulation. So a lot of space industry systems right now are using what's called Mylar. Mylar is basically a thermal blanket which covers important electronic components. There's also unwanted heat, so extreme temperatures up in space, as we all know. This in fact has thermal expansions, material deformation, and overheating of circuits. Again, we can use Mylar to protect those circuits and protect the electronic components. And of course, there's space debris. We can assume that the space debris will not harm the system, but in case it does, They will have like hole penetration and damage, which can in turn damage internals. A mitigation for this is we use shielding, or we make the hole strong enough to protect against minimal space debris.
And so some of the risks for the sensors are going to be micrometeoroids or, space debris. And so the effect that this can have is the loss of functionality or performance, inaccuracy. And so what we're thinking to mitigate this is to find space qualified components. Another risk would be extreme temperature fluctuations. And again, this can affect its performance. We're looking at space qualified components as well to mitigate that risk. And then RJ is going to continue with the communication failures.
For the communication systems, one of the risks is failure for the other devices to communicate with the system. So it's an inability to transmit the data entirely. And to mitigate that, we would have to resort back to either RF communication or store the data until connection is restored. Another risk is corrupted data entirely. So let's say we store that data and it somehow becomes corrupted. We would have to have extra storage channels. And another huge risk, especially in space, is signal noise. And because there's a lot of noise in space, to mitigate that, we would use either signal filtering or resort back to RF communications.
So some risks for the stabilization clamps is continuous motion. So the continuous motion on the gears could cause wear and cause fatigue. So we include variable speed drives to avoid sudden motions. And it'll control speed. It controls the speed for stabilization for the engagement and the de-engagement of the clamps. Another risk is the friction between the gears. This is really important because this friction can increase the energy consumption every time the clamps are being used. And the system lifespan itself can be decreased because the clamps can just fail, right? So a mitigation for this is we use space grade lubricants, again, solid based lubricants like Teflon, and or we make the gear a low friction coefficient material for the gear.
Now, there was an error with the presentation, so we didn't have a slide talking about the welder, so I'll try to fill in the information where we can. But so when we're dealing with the welder, we're going to have like some failures with a power supply, or there could be failures of power supplies, which could actually end up breaking the entire system. And to compensate for that, well, to prevent or yeah, I guess adjust for that, limiting power output so that it's enough to melt the wires without, I guess, overdrawing any power or maybe taking away from critical systems that will be on board. The amount of the wire that we're actually melting is about 2 millimeters in diameter, as well as a 2 millimeters of penetration of the 1/4 inch wire. And this will be basing off of what's currently available, we could do this with about 25 watts, and doing this about 12 points along the surface of the wire would give us a sufficient enough strength for the wires to be structurally sound. And yes, yeah, next slide.
Next, we'll be talking about the risk for the robotic arm. The two main risks are the wear and fatigue and the loss of power to the actuators. The effect of these risks is that it'll cause failure of joints and actuators and the loss of lubrication and a loss of the synchronization with the entirety of the system, as the robotic arm is a really big piece in moving the welder to where it needs to be. And some ways to mitigate these risks are having low friction coatings and space grade lubrication, and also having backup power systems and redundant actuators.
All All right, so really quickly, this is how I was able to determine what kind of size sensors I was looking at for vision sensors specifically. So again, looking at the precision, as one of the key ones, the size, the reliability, the autonomous part, how compatible it is to other systems, and its lifespan. And from all of this, I was able to determine that I can either go with the small or mid-size. For LiDAR, the biggest thing here was precision, space environment, how tolerant it is to space environment, and what is it? The range as well is probably one of the biggest one, because we're dealing with like close range, so anything that's small size is where we went with.
And then when it came down for us to deciding the method of welding, this is a chart here that we took into consideration TIG, MIG, electron beam welding, and the two types of laser welding, which will be continuous and impulse laser. And TIG and MIG, they will have like some splatter that will kind of clutter the area that we're working in. That could interfere with, actually trying to get the laser to hit where we want, or to perform a better weld, actually. And then electron beam welding is it will do everything we would need, but the power consumption for it will exceed what we're actually given as a constraint. And the continuous laser, the continual input of heat along the wire for the distance that we would want it could induce too much heat into the material, and we're a little worried about that, while also having to worry about the power consumption that it could draw from continuously running that laser and trying to perform multiple welds within a certain amount of time to increase our welds per hour is kind of something we wanted to keep pretty high. So when we came across impulse laser welding, to be able to perform precise high power input welds with low wattage consumption, we ended up just going with impulse laser welding. Next slide. And then here is kind of the overall design of our payload. On the left is a video that shows the animations of how the clamps could draw out, hold onto the wire, and then the doors could open up, and then the welding arm with the welder on top attached to it will unfold out, and it can perform its welds. It should be animated. I'm not sure if I guess went through like that, but on the right side we'll be able to see the how it's all going to be put together.
So the next exercise will be the storyboard of the complete operation from pre-launch to function in orbit, to welding. So initially, the satellite will be designed with various optical terminals and all the sensors that we've chosen. And then it'll be integrated into the Atlas V401 launch vehicle, which will undergo various environmental testing, which is usual for any launch in space. And once secured in the payload by being folded down, it will be launched, and during ascent, it will go into the trajectory so it reaches the correct orbit path. And once the satellite is deployed, next slide, sorry, I went a bit ahead. Once the satellite is deployed, we start to establish contact with various ground systems, and the solar panels and the communication terminals, everything starts deployed, and we start doing system checks. Once the system checks are complete, it goes into operational mode. Next slide, please. And once it's in operational mode, the sensors begin scanning the target area. The robotic arms extends and clamps onto the wire we use. Using our real-time sensor data, the impulse laser welder initiates high precision welds, and all of the operations will be monitored and adjusted using real-time optical and LiDAR feedback. And if any communication link in the system fails, the system automatically switches to RF communications, as stated earlier, as a backup. And once the welding is complete, the arm retracts and the system's disengaged, ready for the next task. Next slide.
And with potential incidents being like the failure of electrical components, we could compensate for this by introducing a redundancy, and this will be able to hopefully keep our bot working for the planned 5 year that we hope they could do, as well as recovery efforts being able to be interchangeable and replaceable so that it could stay up there with minor involvement if needed, or if it's too severe and not recoverable, it could also be deorbited so that it could be taken away from the work area. Next slide.
This is where we start going through various communication options and our data handling strategy. Because welding in space requires real-time monitoring and feedback, we designed a robust communication system capable of high bandwidth and low latency transmissions. Our primary link is an optical communication system using a model 922 FP transceiver, transmitting the sensory data and the video feeds up to 1 gigabit per second. And we've included a backup RF transmission path, and we're using an integrated Ethernet-based routing system as displayed on the slide with the model 922 FOM switch. And the required bit rate is about 100 to 200 megabits, with peaks hitting 1 gigabits per second. And during active welding operations, due to 3D vision data and LiDAR input, the system should run autonomously, but it allows for live feedback as well.
Next is system operations. This is just a timeline of our project. We selected a program manager in August 30th. In the beginning of last semester, we chose our operations and capability in the beginning of this semester, define our system requirements in February, complete our trade studies in February as well. And we also did our conceptual design in February. And then we developed the path to the PDR in April 1st. And then our most innovative topics, this is the trade study for the movement mechanism, the spanning from spider bots to like free flying systems. And overall, the robotic arm had the most benefits and the TRL and the highest TRL level. So we went with the robotic arm.
Okay. You guys are just over time. So if you want to just flip through slides in the next 20 seconds, we'll go to questions.
Okay. This right here is just the
that's good. Just put it up there for 5 seconds.
Okay,
And
that's
go to the next one.
that.
We just want to see that you've done it.
So our challenges, our path to our PDR, and then our paper.
Great. Thank you guys. Sorry for rushing at the end, but I wanted to make sure you guys had everything. Do we have questions from the judges?
When you're considering heat, I didn't see any mention of removing heat. You talked about keeping the sunlight off, but your welder and the electronics are going to generate a lot of heat that you'll need to remove. Did you consider that?
Yeah. So we did take that into consideration, and the main source of heat removal would actually be the radiation. And we didn't do extensive research on the electrical components when we're drawing power through the system to see how much heat that generated. But the part itself, with the impulse laser welding, that the heat radiated away from that after each weld would be enough to continue working with the material without overheating it. But yes, we didn't do it for the electrical systems.
You mentioned that you're leveraging work of another group, and that's why you chose 316 stainless steel.
Yeah.
Does your welding process change the behavior of that material when it's because of the on-orbit conditions? Go ahead.
Oh, sorry. Yeah. So the idea is to kind of make it more rigid. So it's kind of becoming a framework, or it could be like the grounds, I guess like the foundations for whatever structure we're going to be building. So if it's something needs to be like, I guess, forcefully applied or I guess worked with, it's not going to be fragile. It's not going to be a giving way in any way. So it's going to be a rigid anchor in space that we could kind of build off of, and hopefully could inspire, I guess, larger space creations or structures in orbit, and hopefully that could improve space exploration.
Thank you.
Do you have any more questions from the judges? And if anyone in the room has a question, we have a minute here. Okay, I think we can thank our team, both those here in person.
Second.
You guys can go ahead and get started.
Sure. Hi, so we are ASTELAR, Aztec Satellite Technology for Extended Life and Advanced Repair. My name is Sierra Casina. I'm the project manager here. Our academic advisors were Scott Shafar and Pablo Machuca, and our cosmic mentor was Harsha. So this is our agenda that we'll be going over today. And here's the executive summary. So we're going to be operating our mission in the GEO satellite belt. Geosatellites currently rank among the most costly space assets, with individual satellites priced up to 200 million and deployment costs reaching as high as 400 million. Due to these high costs, there is an urgent need for sustainable solutions to increase their lifespan and address end-of-life management. Our capability aims to address this. We aim to do solar cell replacements on these satellites. So solar panels degrade up to 8 times faster in space than on Earth. And our life extension hopes to restore functionality and extend solar panel life by 5 to 15 years. While we are docked with these satellites, we also hope to use our thrusters on the Venus Sat Bus to perform orbit maintenance. This mission is interesting because it is part of a larger mission at San Diego State, where a system of 6 of our ASTELAR servicers will be working in conjunction with a depot satellite to perform repairs on 15 of the Intelsat Galaxy satellite line. Currently, we have a prototype that is functional, and our project is following our path to PDR. So team overview, like I said, my name is Sierra Casina. I am the project manager and the trajectory design lead. On the aerospace side of things, we have Liu Tesfaye, our GNC lead, Juliana Molina O'Brien, our communications lead, and Su Su, our launch systems lead. And then I'll hand it over to Hector to introduce the mechanical engineers.
Yes. Hi, I'm Hector. I'm the mechanical engineer lead. And right now we have our payload lead, which is going to be Fred Ferreiro, MD. which is our power lead, and Lincoln, which is, William Fisher, which is our propulsion lead.
All right, and then here are the dates where we hit our system engineering milestones. So I was selected as project manager in early September of last year. We defined our operation and capability as well as the system requirements in October of 2024. We conducted our trade studies throughout the month of November 2024 and finalized our conceptual design in mid-December for our end of semester reviews. We've been working on our prototype throughout the spring, and we defined our path to PDR in March 2025, and that is what we are currently working on as well.
Hi, my name is William. I'm the propulsion lead. And so at San Diego State, we are required by our senior design project to create a prototype. I know a prototype is optional in this competition, but we were awarded a budget of $6,000 by the Student Success Fee program at SDSU. And we do have a functioning prototype currently, and we've only used $2,400 of that, of the $6,000. So $1,500 of that was designated for travel, so hotel fees, food, stuff like that. And so I gave us an allowance so we have an allowance remaining of $2,100. And obviously you want to do less with more, right? Or more with less, sorry. So we're doing well on a project and a bill of materials. You can see on the bill of materials that the robotic arms take up a large portion of how much we've spent, because we wanted to go for 5 degrees of freedom, because we wanted to pick up horizontally and vertically facing objects while we're in space, solar panels, for example. Okay.
This chart outlines our team's full schedule across 2 semesters. We started with research and design planning in the first semester, moving through background studies, system documentation, and both preliminary and final design. The second semester focused on execution, started with procurement and inspections, then transitioning into manufacturing of the battery bracket, robotic arms, and aluminum housing. Once fabrication was complete, we moved into testing. This included training the object recognition system and evaluating the robotic arm motion with weight capacity, path planning, and accuracy test. Each phase was carefully scheduled to maintain momentum and ensure that all subsystems came together smoothly for the final integration. Then we're moving to systems engineering.
So for our objectives and requirements, our BCT Venus satellite bus and proposed mission, we have 2 primary objectives. The first one is to perform life-extending services to active satellites by replacing solar cells on active satellites. And our second one is to be in operation for the entirety of our 5-year mission. Our secondary objectives include decreasing the amount of new space debris and demonstrating the concept of an autonomous repair vehicle that specializes in repairing and updating satellite power systems. In the table are our BCT Venus satellite bus requirements. The mass is going to be 70 kilograms. The volume is going to be 17 inches by 16.4 inches by 27 inches. Our power available is 444 watts. Our power storage is 10.2 amperes. Our point of accuracy is plus or minus 0.002 degrees for 3 axes and 2 trackers, and our delta V is 7,000 meters per second. For innovation and impact, our proposed mission, our innovation is targeted in a number of ways. So satellite solar cell repairs. Previous successful ISAM missions have focused on refueling. The larger mission is designed to service 15 telecommunication satellites in 2 clusters. And on the bottom image, you can see the 2 Intelsat Galaxy clusters. We are utilizing a centralized depot for refuel and restocking, like we've mentioned previously, and we're utilizing AI damage detection to do so. Our impact will be to increase satellite mission time, which will improve cost efficiency and ensures continued service without premature replacement of these Intelsat satellites. The cost to develop, manufacture, and launch a new Galaxy satellite is around $300 to $500 million per satellite, which totals about $3 billion, which means that we will be profiting $4 to $6 million while saving companies $2.25 billion in replacement costs. In the top image, the black image, you can see that this is the prototype of our depot, with 6 different servicers connected to the middle ring, which is the docking. And on the far right is the Galaxy 33 satellite, which is just one of the 15 Intelsat Galaxy satellites.
So here's the storyboard of our complete operations. So on, I think it's your right here, you're going to see the larger missions operation phases. So our servicers will be traveling with this depot from launch and insertion into GEO at that first cluster. Once it is in that cluster, it's going to move on to the servicer operations you'll see here. So it will receive mission data, which is going to be which client satellites each servicer will be targeting and their current condition and whereabouts. From there, it will undock and begin its mission. Once it docks with the client satellite, it will determine safe operating conditions. From there, it will move on to the AI solar panel detection, so it will be detecting any damages. From there, removal of the damaged panels and replacing the damaged panels with our new solar cells from storage. Once it has secured the connection and ensured that it is functional, it will undock. From here, it will either navigate back to the depot satellite or it will continue on to the next client satellite depending on a preset plan. Once we have finished our operations in cluster 1, all of the servicer satellites will return to the depot and dock. From there, it will phase to the second cluster, continue this the same operations. Once all of these satellites are complete, we will either continue the mission with new client satellites if we have enough fuel and parts, or we will do our end-of-life operation where we send the entire system into a graveyard orbit. So one of the major trade studies we conducted at the beginning of this project with the larger AE mission was whether or not we wanted to be doing this in LEO versus GEO. So in recent years, there has been an increase in developing technologies in refueling and life extension, which are mostly focused in GEO. This is because GEO satellites are over 14 times more expensive than LEO satellites. As stated by Carl Stoles, from the Air Force Research Laboratory, it's cheaper to just build a new satellite and launch one and dispose of the old one than it is to actually try to refuel it. The strength is in the GEO market.
Another major trade study that we completed was for the robotic arms themselves. I touched on it a little bit earlier, talking about 5 degrees of freedom to pick up horizontally and vertically opposed objects. And from this chart that we have here, we went with the Lynx Motion SES V2 because it fits our criteria. It had the highest reach out of these 3 robotic arms that we're comparing to. The cost was middling. Obviously, it was not. The one on the bottom here is very expensive. And since we are on a tight budget with our prototype, I thought this would be good enough. The Lynx Motion SES V2 is a modular design, so parts are replaceable easily. It's just a couple screws and get a new servo or whatever. It is so the 5 degrees of freedom, we have a wrist rotation, which allows us to move, obviously the wrist, to pick up these horizontally or vertically opposed objects. It can also rotate 360 degrees around the base. So we can pick up a solar cell and then place it in a storage unit inside the box, or inside of our payload, I mean. And they do fold down into a pretty nice compact size. So we're not worried too much about taking up a lot of volume inside of our payload. Yeah. Thank you.
So the feasibility of our mission, this is based off of the analysis done of the prototype and analysis of the larger mission planned to service those 15 Galaxy satellites. So currently we've used about 19 kilograms of our payload. And then later on, we'll go into the CAD model showing that we are within the allowable volume. Our power is currently under 10 amp hours used. And our Delta V budget is currently well under the 7,000 set by the Blue Canyon Technologies satellite bus at 1,400 meters per second.
So moving on to the risks, in the table below, each risk is designated a cube number based on the likelihood and impact of it happening. Following necessary mitigation steps, the risks move across the chart to lower levels of criticality. In the risk cube matrix below, the bold and underlined numbers represent the updated risks after mitigation. So we do have 5 main risks. being if the robotic arms fail to actuate, if the battery fails or dies, if the opening door mechanism fails, if the wiring notices a fault, and if a collision occurs. The likelihood of these happening ranges from low to medium, but after post-mitigation steps, it does move it down to low. And then just delving deeper into the risks, we do have pre-mission testing, which is performing extensive actuator performance and redundancy tests, conducting stress tests and life cycle analysis on the batteries, testing the mechanical door components for wear and tear, inspecting all wiring connections for integrity and shielding, and then simulating collision scenarios during pre-mission testing. We do have a software-based analysis as well as a manual override and a mission abort in case any of the risks become a possibility.
This third matrix is going to be based on the holistic mission, which is going to be based on both the depot and the servicer. Some of our most important or most critical risks are going to be separation failure, which in mitigation strategy, we'd be using key joints so that if anything were to happen, we'd be able to operate or be able to separate on command. Something else that we wanted to really emphasize on is the debris and docking collisions. If another mitigation degree strategy that we're going to utilize is figuring out collision avoidance maneuvers so that we can move either the servicers or depot away from said collisions.
And here we're going to start going into our systems design.
So for data handling and comms, we have two main requirements: that the data rate needs to support continuous real-time operations, and that the bidirectional relay of information between the service satellites, the servicer, the depot, and ground stations is continuous. And this is in support of four main objectives: the transmission of health data from the Intelsat satellite to ground stations, verifying the servicer is carrying the necessary tools, solar panels, and sufficient fuel to complete its mission, and proper docking, which will be supported through real-time video transmissions, as well as passive debris tracking, which is going to be occurring 24/7. So as you can see in the image, this is a high-level overview of the communication links. The servicer will operate in X-band, in uplink and downlink to ground stations. The depot will operate in X-band for downlink and S-band for uplink. And intercommunication between the servicer and depot operates in S-band. So as we've said before, our mission supports Intelsat Galaxy satellites, which communicate via ground stations rather than with each other. So for our mission, were something to go wrong with Intelsat Galaxy satellite, it would send a message to the ground station. The ground station would then relay that message to the servicer. The servicer would determine whether it was carrying sufficient fuel, proper tooling, and equipment to complete the mission without having to access the depot. At which case it would either go to the Intelsat Galaxy satellite or it would return to the depot for this equipment. During docking between the satellite and the servicer, there will be real-time video transmissions to the ground station. And after servicing, a health data report will be sent to the depot, which will be compiled with other data and transmitted in batch data weekly to the ground station. So this is, like I said, we're operating in S and X-band, S-band for telemetry tracking and command control, reliability for lower data rates, and X-band for high data transmissions, which is necessary for debris tracking and real-time data exchange. So we have determined 5 different ground stations, and this is because the services are operating in phasing orbits, which means that multiple ground stations are necessary for global coverage and redundancy. The depot will consistently be over South Point and Clewiston. As you can see on the right-hand side, we're operating in KSAT and SSC. On the bottom 2 images, these are 2 antenna capabilities in particular that are provided by the BCT technology, well, Blue Canyon Technologies, that we agreed fit the requirements of our mission. So, and more will be on the next slide for that one. But operating costs for the antenna use per hour, year is not available online, as this is all private information. But after minor calculations, we also have determined we do need operators in the ground stations 24/7. And the cost for this, for all 5 ground stations per year, on the low end is $216,000, and on the high end is $300,000, so well within our budget. This is the chart that I was talking about, and this is a summary of communication components. The top 2 in the chart on the left are going to be based on the images you saw on the previous slide for the BCT antennas that they provide. As of now, we want to use both just because our depot is operating in SN X-band and our servicers operating X-band. So it'd be easier for latency and redundancy purposes to include both. And as of now, they're both well within our budget. And then on the right hand, in total, our communication mass will be between 29 to 68 kilograms. Our sizing will be 22 to 22.57 meters cubed, and that is because the X-band sizing in the S and X-band all-metal patch antenna is a little bit larger than its alternatives. The power will be between 98 to 244 watts, and our cost right now is between 5.6 to $22.6 million. On the right-hand side is a summary of the data rates required for each subsection. So for GNC with supporting systems and payload, right now we are looking at 0.5 to 2.5 megabytes per second. For real-time video transmissions, which is going to be essential during docking, we have 1.1 to 8 megabytes per second. For real-time communication, 6 to 8 megabytes per second, and then debris tracking after compression is 0.3 to 1.4 terabytes. And we have decided to reduce transmission volume and processing costs associated with ground-based processing through introducing onboard filtering on the satellites. And that is because we've determined that for real-time video transmissions, we needed 30 to 60 frames per second, which resulted in the numbers you see in the chart. And going through those other numbers that I just described, that comes out to a lot. So we figured that we can lower this by 50 to 90%. Especially during debris tracking after compression, which is in terabytes right now. That'll be reduced to 0.3. So these are the lower costs. Before them, they were 3 terabytes per day. So if we lower them to 0.3 to 1.4 terabytes per day, we can send those in batch data down to grounds every 3 to 5 days.
Now, for guidance navigation control, we know that for the servicer's most critical phase is during close proximity operations. So that's when the depot is either refueling or when the servicer is being refueled at the depot and when the servicers are heading to the client satellites for servicing. As we know, the Venus class bus already includes an attitude control system, reaction wheels, gyroscopes, and star trackers. However, we believe that we should include 2 more instruments so we are able to fulfill our requirements down below to be able to detect and track our client vehicle and depot from 50 kilometers and maintain a spectral range from 400 to 900 nanometers for close range inspection. We are including the LiDAR sensors for long range detection, which is able to fulfill our first requirement, and the Astro head camera for the close range inspection, which is able to fulfill our second requirement. And these operations will be autonomous. But if something were to happen and risks arise, we're able to connect from ground to manually operate.
For the launch, we're looking for a rideshare for 6 of the Venusat buses, which each will include the design payload. And rideshare from SpaceX Falcon 9's rocket is the most ideal with its lower cost compared to the Atlas V. And Impulse Space also offers reliable and cost-effective rideshare launches to geostationary orbit as early as 2027. Next slide. The left image shows the configuration for rideshare from SpaceX, and the right is the estimated rideshare costs. The max payload at 70 kilograms has a total launch cost of all 6 of the payloads at 2.5 million to 3.5 million. But with our payload mass of 20 kilograms, the total launch cost is just below 1 million.
All right, so here's the trajectory analysis for our proposed clientele to make sure that we're within that 7,000 meter per second delta V budget. So if you see here in the table, we have cluster 1 and cluster 2. Those are going to be the 2 main stops that we are servicing satellites at. You can see the servicer numbers are going to be down on the column. Some of them are going to be going to multiple satellites. Those are going to be multiple uninclined client satellites. And some of them are only going to 1. In the case that they're only going to 1, those are going to be for the inclined client satellites. And that is due to the increased delta V usage when making an inclination change. The chart over on the right here is going to show the different delta V allotments for each servicer on the different clusters. So the blue cluster will be, or blue will be cluster 1 and red will be cluster 2. As you can see, we are staying well within our allotted Delta V budget, which will allow some extra room for any maneuvers we have to do that we do not foresee, and station keeping while we are on or docked to the client satellites. And here we have a, so here is going to be what should be running an animation of one of the trajectories. This would be a complete transfer from the depot satellite. It would perform a Hohmann transfer to get to the approximate shape of the client satellite, at which case it would travel to the radius of the ascending node of the client satellite, where it would perform its inclination change. After it performs its inclination change, it will wait until it is at periapsis, at which point it will perform a phasing maneuver, which will change the orientation of the orbit and have it rendezvous with our client satellite. And then you can go back to the presentation.
So going back to what the servicer is going to be focusing about, since we're focusing on solar cell replacement and damage recognition, that's the main focus of the project, and the prototype is mainly to integrate those two capabilities into one autonomous system. Here we have the layout of our prototype, which at the bottom we have the satellite that's being serviced. The dotted lines are the implied lines, which is gonna be always on loop. For the Raspberry Pi, it's connected to a camera, which is gonna be detecting the solar cell and also detecting the damage on the solar cell. And the Arduino, it's gonna be controlling the robotic arms, which that's gonna be controlled by the Raspberry Pi. So going now to the prototype, we're focusing on those two.
You guys have to kind of cut to the chase and just run through your slides quickly, so you can do them.
So we have the prototype components.
I'm gonna cut you off in 1 minute.
Yeah, prototype components, the damage detection and the manipulation of the solar cells, the DMFA, our CAD components also. Lessons learned.
So these are the biggest challenges we encountered. Here are the most innovative options. We considered refueling, soldering, and using electromagnets for docking. As far as technology gaps, docking was a technology gap we found, as well as the robotic arms, their dexterity and autonomy, along with using AI learning. And then our past PDR that we are currently on, improvements on the camera's robotic arm dexterity for the prototype, as well as bridging technology gaps like the docking process and close proximity sensors, and then more thorough analysis of each subsystem. Thank you.
Okay, now is the time for our judges to ask questions.
Realizing that it's not quite in the core of the C3 data that we look for, I question the cost of having 24/7 operators at your ground sites at only 200,000. And let me tell you why I question that. You all will be graduating soon, and you'll expect to make somewhere in the neighborhood of $100,000 a year. So if we hired 5 of you, how much would that cost us?
So I agree that the number should be closer to 500,000 at 6 figures per person per ground station. The highest operating costs were obviously in Clewiston, Florida, in South Point, Hawaii, where you're getting paid livable wage, and in Germany. Those were the highest costs. So you were looking at Clewiston and Hawaii, upon research and cross correlation with research that we conducted for our actual class on the depot, operators are only paid about $60,000 to $80,000 a year. And in Japan, when you convert that to US dollars, it was about 40. For India, it was on the high end of $20,000. And in Germany, it was on the high end of about 80 as well. So I actually think I miscalculated a little bit, but it's not much higher than that. It's maybe around $400,000 because of the lower costs in India and in Japan.
You also want to account for your overhead costs of employing people.
You are right.
Thanks. I got one right today.
You're replacing the solar panels. I didn't see anything with respect to how you're going to connect them, the complexities of actually connecting the new panels.
Yeah. So some of the stuff we found in that was that a lot of them are using simple, I'm forgetting the word. It's basically a simple metal connection. So we're planning on having our replacement solar panels have a connector slot for the old connection to go into to maintain, to keep it working.
Yeah, I want to add on to that. Right now, most of the research that we did on solar cell replacement, they mainly replaced the whole array, not a single solar cell. So yeah, like that would be like added to our path to PDR in future state. So yeah.
Okay, I have one question. Did you hear about any shaking on campus? And are you sorry you missed it?
Yes, we did hear about shaking on campus. 6.7.
7 after, I think they redid it to 6.2 after further investigation, but it was pretty large.
But yeah, all of our phones are going off
Simultaneously.
about
Well,
campus
I
flooding.
hope there was no damage to the campus. And
So as of right now, there's no damage.
okay, so we've reached lunch here. So the Zoom is probably going to go on pause. It'll probably stay open, but we'll stop screen sharing, and we'll be back. I think it will be back at 1:15. So we got about an hour and 10-minute break. Thank you, everyone. Okay, the clock here says 1:14, which means it must be 4:14 in State College. So why don't we get started with Tri-State Horizon?
Hi, I'm Rachel Krug, and we are Tri-State Horizon from Penn State University. Today, we'll be presenting our payload Orbital Catch and Release for the Cosmic Capstone Challenge. The problems that we focused on were spacecraft collisions caused by space debris, the serviceability of this debris, and orbital sustainability. We researched previous technologies that attempted to mitigate this issue and found that it is difficult to capture the debris without causing more damage due to the irregular shapes of the debris. Without effective debris removal, future space missions may be more costly and dangerous due to the requirements to avoid existing space debris, but also any ISAM technologies that might generate space debris could use this method to assist in post-manufacturing cleanup. We propose a payload with 3 operations in the order of soft capture, hard capture, and release that will catch and release debris to bridge this capability gap and hopefully in the future allow this debris to be reused. Currently, this payload shows our work done proving the concept and demonstrating the mission. The team consists of Ashley Loftus, our team lead, Wesley Green, myself, Rachel Krug, Brandon Giro, Liz Glenister, and Braden Johnson. We've been working on this payload over the past year, and our project milestones include the following, where we have our preliminary design review and final design completed on April 1st. Along with these major milestones, we also completed project scoping, functional architecture, requirements generation, and subsystem design over the past year.
Early on in our process, we were inspired by a future in-space recycling system that could use a station that could use decayed satellites, and this drove us to have this catch and release design where we'd be able to take debris and move it to the recycling station or a safer orbit without damaging it. To develop our design, we came up with 3 initial concepts. Each one had a hard capture system, a robotic arm, or soft capture system, and an end effector. The first concept had inflatable pneumatic fingers as the end effector attached to an inflatable pneumatic arm. And we used several arms that we called cage arms to hold the debris in place as our hard capture system. Our second concept had a magnetic end effector on a Canadarm style robotic arm and had a crab claw-like hard capture system. Our third concept had a end effector using NASA's Gecko Gripper material attached to 2 simpler robotic arms and a hard capture system that was a multi-pin pressure sensor chamber. We conducted a trade study to assess the hard capture system, soft capture system, and the end effectors from each design against each other by their functionality, reliability, cost, complexity, manufacturing difficulty, power consumption, technology readiness, and mass, and then down selected and combined based on these results. Ultimately, the components of the third concept won in all 3 categories and provided most of the basis for our final design.
Here's the complete storyboard of the complete operation. First, we're going to launch the spacecraft to its desired orbit. Once it's in its desired orbit, we're going to deploy it and rendezvous it with the space debris. Then the spacecraft is going to orient to align with the space debris. Once it's aligned, we're going to demonstrate the soft capture system. After the demonstration of the soft capture system, we're going to demonstrate the hard capture system. Once the debris is captured, we're going to maneuver the spacecraft to its desired orbit and release the space debris. And then at the end of the mission, we're going to deorbit the spacecraft.
The micro-level mission architecture goes into depth over our 3 autonomous operations: soft capture, hard capture, and release. These first 3 steps demonstrate soft capture. After the spacecraft rendezvous and orients with the debris, 2 robotic arms are deployed from the primary structure of the payload, and these 2 robotic arms perform soft capture by connecting to the debris with 2 Gecko Gripper end effectors. Using a Gecko Grip end effector lowers the risk of damaging the debris during capture.
Yeah, next slide.
So this is an animation we have here. Should pop up a little play button if you want to click that on the slide. So this animation details the deployment of our soft capture system using the long robotic arms with a arbitrary debris piece in the center that they grab. The robotic arms using NASA's Gecko Gripper technology are integrated into the end effectors of it to be able to pull in the debris to ready it for hard capture. Next slide.
Next steps demonstrate autonomous hard capture. The robotic arms pull a section of the debris into the multi-pin pressure sensor chamber. The chamber deploys a total of 416 pins at multiple angles, and each pin is employed with gecko grip material at its tip and individual pressure sensors at the base. For an individual pin, once the pressure sensor detects a certain set pressure, the pin stops deploying. This mechanism allows the pins to mold around irregularly shaped debris. Once all the pins are deployed, the robotic arm end effectors detach from the debris by rotating. Then the robotic arms are then stored back inside of the primary structure of the payload.
And here's the second part of our animation. You can click play, and this details the arms moving in the object, and the pressure sensors are going to conform to the size of the debris, and then these pins will have sensors to not damage the debris, so it'll have just enough force. And you go to the next slide.
The last steps demonstrate autonomous release. After the spacecraft maneuvers to the desired release orbit, the robotic arms are deployed and reconnected to the debris. The pins inside of the chamber rotate to detach the gecko grip material, and once all the pins are retracted, the robotic arms pull the debris outside of the payload. And once the debris is outside of the payload, the robotic arm end effectors twist to detach from the debris. And once the debris is released, the robotic arms are then stored back inside of the primary structure of the payload.
So here we have a drawing sheet of our payload, including important dimensions to show how our design model is set inside of a cylindrical housing, and that the design is completely self-contained within the volume limit of 123,276 centimeters cubed, specified in the RFP.
This is our system decomposition diagram showing the breakdown of our design and which team member designed each segment, element, and subsystems. Not shown in this diagram is the CAD segment done by Brandon Giro and the orbital analysis segment done by Liz Glenister. To select a launch vehicle, we completed a trade study which shows how we compared 3 possible vehicles: the SpaceX Falcon 9, the Northrop Grumman Antares rocket, and the Northrop Grumman Pegasus. Each vehicle was compared based on the requirements shown, where the vibrational displacement was calculated from each vehicle's maximum launch acceleration and frequency. From this trade study, it was found that the SpaceX Falcon 9 would be the best launch vehicle for this mission.
Our orbital analysis was largely based on what our target debris orbit was. Particularly, we had selected the electron kick stage with the tracking number 60420, since it was in a not too inclined orbit and was a object of viable size. So the target debris orbit we used for most of our power, thermal, and communication system development for that initial analysis. And we also had a set up an initial orbit approximated off of common Falcon 9 launch orbits, and a final orbit as the demonstration to move the debris into a second orbit, and use this to calculate the fuel requirements to make sure we had a acceptable fuel margin for other maneuvers as might be needed. And then if you advance one, a image of our SDK analysis showing the piece of debris and the coverage of our selected ground stations.
For our communication and ground systems, we conducted a trade study to figure out which ground system would be best for our mission. We chose criteria such as gain to noise temperature ratio, bandwidth, coverage, and number of locations. And while our mission will be autonomous and we won't need real-time downlinks and uplinks, the team decided that they are wanted in the event of an autonomy failure. This mission will likely require an observer. However, this should not be a difficult task because the ground system that we went with, Leaf Space, features a payload and spacecraft operation control center, as well as a mission control center with remote access. We went with S-band communications because that's what our satellite was capable of and what's standard for low Earth orbit. And we allotted 30 watts of power for downlink and 2.5 watts power for uplink. And this gave us the ability to receive and transmit data with the ground system at a rate between 1 to 5 megabits per second. We chose 3 ground stations from Leaf Space, and the link budgets were conducted for each one of those. And we aim to have a link margin between 5 and 20 decibels, which can be seen there on the slide.
For the bus and payload thermal subsystems, we first conducted research to find the maximum and minimum temperatures for all the materials and components, from which it was then found that the internal temperature of the bus and payload needs to be kept within -19 to 40 degrees Celsius for efficient operation. To do this, we selected a Temco silicon heater attached using pressure-sensitive adhesive to the integrated end of the payload that will be controlled autonomously with 4 thermistors, 2 in the bus and 2 in the payload. Then additionally, a trade study was conducted to select which thermistors will be used, and radiative heat transfer analyses were done in MATLAB to determine the change in temperature from the sun while out of eclipse.
For the guidance, navigation, and control system, we ultimately selected Blue Canyon Technologies FlexCore, specifically using 4 RW8 reaction wheels in its configuration. We selected this through trade study with other Blue Canyon Technology solutions, particularly the Exact 50 and Exact 100 systems, and determined that this was the best option that would provide sufficient precision and torque for the maneuvering that was necessary.
Here we have a basic overview of the command and data handling system. The bus computer will receive commands and send telemetry to the communication system. Additionally, it will also send commands to the guidance, navigation, control system, the power system, the thermal system of the bus, and the propulsion system. It will also be interfaced with the payload computer, which sends commands to the optical tracking system, the thermal system of the payload, and the robotic arms and pin chamber.
For our power storage, we're using 6 2P8S and 3 1P8S batteries from BCT. The total battery capacity on board is going to be 1,188 watt hours or 40.8 amps. And it's going to be enough power for our delta V maneuver and attitude control, and have a delta V of about 450 meters per second, so it can be fired for about 1 hour. And for our propulsion subsystem, we went with the Orbion Aurora thruster system. It's going to be a design which uses a dual mode system using xenon propellant to do both cold gas type attitude adjustments and Hall effect orbital transfers. Our design includes 6 of these thrusters, producing between 2 to 2,000 millinewtons of thrust in any direction.
Using the provided payload volume constraints, the dimensions of the payload primary structure were set to a height of 50.8 centimeters, an outer radius of 23.91 centimeters, with a wall thickness of 1/4 centimeter. After doing a trade study, the material selected for the bus and the payload was aluminum 6061, and also structural analysis was done to ensure that the structure can withstand launch loads.
We added a optical tracking system to our payload in order to be able to determine the relative position, orientation, and velocity of the target debris. So that way we'd be able to safely perform rendezvous, capture, and release operations. Particularly, we selected Abruta's rendezvous, proximity operations, and docking, or RPOD kit, as our optical tracking system.
We also created a mass budget based on the components needed for each subsystem of the bus and the payload. As shown, the total mass of the system is 69.97 kilograms, with the bus having 69% of the mass and the payload having 31% of the mass. There is also a total of 10% of reserve mass split between the bus and the payload.
Our power budget breaks down the nominal voltage and peak power of each subsystem. We have considered a reserve of 30% into our total power budget to accommodate any extra in case of needed maneuvers during the mission operation.
The team defined several potential risks to our mission and developed pre-launch and during launch mitigation strategies. So our first risk involves missing the launch window. Obviously, before the launch, we will make sure that we know what our launch window is, and we will also determine what the next possible one will be. So if we do happen to miss it, we can wait until the next launch window or determine a new launch site. Our next risk involves a delay in the Gecko Gripper technology. Currently, it's set to be at the highest technology readiness level at the end of the decade, which is when our mission will launch. However, if there is a delay, we will either have to delay our mission or we will switch to a different end effector involving magnets. Our next risk involves a pin pressurization failure. And so our multi-pin pressure chamber is designed to be individually pressurized. So if there is malfunction in one of them, it should not affect multiple. And so for in our hard capture sequence already, we have death code programmed to override and just stop the function of that pin. That way it doesn't damage the debris or cause any other issues. If we're already out of our hard capture sequence, then we could just cancel the release stage. Our next risk involves potentially missing the initial rendezvous with our debris. Before launch, we will obviously make sure that we have our calculations checked and make sure that we're good to go. However, if something does happen and we do miss it, we have enough fuel on board to make one maneuver to realign and still complete the mission. Our next risk involves causing damage to the debris. Obviously, the whole point is we want to mitigate the debris in the orbit, so we don't want to cause any more, but we've designed our mission to have a precise attitude adjustment system to avoid that damage. However, if something did happen, we would have to reevaluate our mission and determine if it can still be continued or if it's just failed. Our final risk involves an autonomy failure. I talked about this previously on the communication slide. We want our mission to be autonomous, but if something did fail, then we have continuous communication available with the ground system if needed, and we could manually complete our mission. This slide shows our risk mitigation matrix. For our mitigation strategies, it shows that the likelihood of these risks don't decrease. However, the severity does. And so if these risks were to become an actual issue, the severity is less and therefore it should not hinder our mission as much.
Here we have a few technology gaps that, if closed, would benefit our mission. First, the Gecko grippers not being completed. As of right now, they have not been tested in the environment that we are planning on using them in. So once those are completed, it would increase our mission confidence and allow the mission to proceed as planned. Additionally, the development of an in-space recycling system, having a recycling space station in orbit that we can move the debris to for recycling would make this mission more impactful and increase the reusability of the debris. And also being able to utilize magnets. Right now, not all space debris is magnetic, so using magnets isn't feasible. But if we were able to magnetize debris, we'd be able to use magnets in the capture system. Here are some of the biggest challenges we encountered during the design process. One of the big problems was integrating the payload with the Venus class bus. It seemed like we didn't have a lot of information on the Venus class bus, and it made it difficult to be able to integrate what we were doing in the payload with the bus. Similarly, it was also difficult to access detailed information about each subsystem and system. Some of us had to reach out to companies to get info, and when that didn't work, we had to select new mechanisms when we couldn't find information that we needed. And finally, having a limited mass and power budget was also a challenge. We had to make sacrifices to the payload and reduce the factor of safety to make sure that we were in the mass budget and the power budget.
The first of the lessons learned that we learned early on was during our research was how much space debris there is, the scale and growing scale of the problem, and the need and how new ISAM capabilities will be able to mitigate it. This is what inspired us particularly to select to develop the catch and release payload as a means of mitigation. We also learned why finding and planning for risks is important to prevent mission failures and having redundancy measures, so that way, a component we expect to fail won't holistically end the entire mission. Find ways to work around it and either have partial success or still complete the mission. We also learned how critical system engineering is to a mission to ensure that all parts work together, ensuring integration and that budgets for mass and power are met for the mission, and that these systems interact in the way that we intend them to and don't get in each other's way was a challenge, and I think we learned a lot through it. For our paper, we formatted it according to the IEEE Aerospace Conference in Big Sky on the 1st through 8th of March in 2026 for publishing. Our abstract was 160 words. Our paper length in total was 20 pages, and we included 33 references.
As shown throughout this presentation, our team completed design work to integrate our payload with the BCT XSAT Venus class bus. We created a mass budget and a power budget that includes needed parts and power for integration, as well as completed the subsystem design and analysis work shown prior. This work was done to ensure our payload and the bus can successfully integrate and complete this mission. Recommended future work includes increasing the payload and/or the host spacecraft size, which will then increase the mission possibilities and increase mission safety. Develop the payload with the host spacecraft designed to verify integration. Increase the power generation to increase mission possibilities. Explore combining magnets and gecko gripper as an end effector to reduce risk from possible gecko gripper technology delay. Complete a cost analysis to verify mission costs and possible profit. And lastly, finalize the launch window to verify rendezvous with the debris.
Our mission, Orbital Catch and Release, uses 3 autonomous operations, soft capture, hard capture, and release, to demonstrate ISAM capabilities. Our innovative design that has 2 robotic arms, gecko grippers, end effectors, and a multi-pin pressure sensor chamber allow for a gentle approach to capturing irregularly shaped debris in low Earth orbit and releasing the debris into a graveyard orbit. The ISAM impacts of our payload design include debris removal, space situational awareness, and sustainability. Are there any questions?
Okay, we'll open it up to our judges for any questions.
Can you give us kind of a scale, the size of the debris, the mass of the debris that you're after? And how does it compare with the spacecraft?
If you want to continue to the background or to the backup slides, to the requirements slide, it shows the if you look at the first requirement there, R1.3 and R1.4, it shows that the debris will be within a 300 to 500 pound weight range and within a 0.5 to 1.5 meter width.
Have you done any analysis or are you concerned with tumbling debris? Any momentum that the debris can carry itself?
I'm sorry, could you repeat that question?
If you have a debris in space, it's most likely not controlling its orbit. It's probably dysfunctional. It may be tumbling. It carries a momentum. Have you done any analysis of how to deal with that?
Not particularly for this demonstration. We mostly just focused on the piece of space debris that we selected.
Yeah, and speak to on the guidance, navigation, and control side of things. Part of that was trying to maximize the maneuverability to be able to interact and handle that momentum. But we found limited data on the tumbling effect of debris, so we did not yet commit too much time into figuring out exactly what measures need to be taken, what exactly requirements, and like what range of pre-existing tumbling would we be able to manage. But that'd be a good spot for future work.
Thank you.
A question on the line. Can you hear me?
Sorry, could you repeat that?
Vinay here. Can you hear me?
Yes, we can hear
Go
you
ahead,
now.
Vinay.
Oh, yeah. So the question I have is relative to the grip mechanism itself. So is it like a pad with some sort of friction coefficient? Basically, how you because you're pinching it almost. So I'm just trying to understand what kind of force and frictional force you need to actually grab it, depending upon
Yes. So the end effectors on the robotic arms have the gecko grip material that's currently being researched. And it's basically a bunch of fibers on a circular flat pad. So when it makes contact with the debris, it sticks to it. But so it requires a very little force to connect and to detach it. Each of the individual fibers can detach at an angle of 25 degrees. So by rotating the end effector, they can be detached that way. And then the gecko grip material that's inside of the pin chamber, it's a very small piece on each of the individual pins. There's a total of 416. So in the pressure sensor, it only allows the pin to deploy it until the pin makes contact with the debris, and then the pressure sensor lets the pin know to stop deploying. So it's not that much of a pressure to so it doesn't damage the debris.
Yeah, okay. I understand it, but are you using the gecko material that was recently tested in the ISS or a different kind of material?
That material, yes.
That very same material. Okay, that's an excellent material because it's good for radiation environment. So thank you for answering. Appreciate it.
Thank you.
Yeah, hey, I just have a quick question. So you kind of have this two-step capture process, and both of them are have pretty intricate systems to do it. Have you all looked at, and I see you have a requirement that requires you to do both of them, so maybe you didn't, but have you all looked at, could you do it with one or the other to simplify the overall system, or is there a reason why you felt you had to have the two-step process?
We have the soft capture and the hard capture because we're maneuvering to a new orbit. So it would be more stable to have like the arms initially grab the debris and further stabilize it by moving it into the chamber, and then storing the arms back inside for the maneuver to the release orbit. So we haven't looked into one or the other necessarily, but the purpose of having both is to stabilize and reduce risks.
Okay, thanks.
Thank you.
Okay, I think we can thank our speakers, and we'll start the next team in 2 minutes. Okay, Team PRISM, you guys are welcome to get started.
Hello, can you guys hear us?
Yes.
Cool. Is it all right if we present locally on our end?
If you think there's a need, we can do that.
Yeah, we're all in a conference room together. It'd be a little better for us to transition and such.
Okay, go ahead.
Alrighty then. Welcome, everyone. We are Team PRISM. This is our final briefing for the payload for remote and space maintenance, also known as PRISM. Kind of give a high-level overview of everything. Our problem is that we're trying to resolve battery failures in satellites by installing an external auxiliary battery to a pre-existing umbilical port. Our test case will be the Neil Grice Swift Observatory. The outcome from this operation would be to extend the satellite's current lifespan by giving it another battery to charge and pull power from. Throughout the entire time working on this Capstone project, we developed ConOps, designs, mass power uplink calculations, and a CAD model to kind of show our design for you all today. Then our next steps are to do an FEA analysis, then develop a full-scale physical prototype. But before we get into any of that, this is Team PRISM. We'll all be presenting today through Damien's Zoom, and we're very excited to show our payload for you all. So kind of give some background on the team. We were formed in late August, and since our formation, we started off by doing some project scoping. Based off that project scoping, we developed our functional architecture that led into our top level mission requirements, that then went into our system operations capabilities. From those operations capabilities, we split our team into 3 small teams to do 3 designs at the end of last year. In the beginning of January, we kind of did a bunch of trade studies to down select to one design. This is the one design that we'll be excitedly presenting to you all today. So to kind of give an overview of our mission, according to a University of Maryland study, about 13% of satellite failures are due to battery failures. And we want to mitigate that by installing auxiliary batteries to target satellite. So for our mission overview, we're using the Neil Grice Swift Observatory as a proof of concept. As Team PRISM, we took the initiative to reach out to Swift's director and operators as we wanted a real target satellite to base our proof of concept mission on. With their approval, it was basically a prime candidate for an external battery installation. It's a scientific satellite that by going down, it'll cost a lot of money to replace. And using something like an external battery system to make its lifespan longer would have a lot of beneficial means for both economic and scientific. We didn't really want a satellite that would be an ideal best case scenario. We wanted a realistic challenge that would show realistic use of in-space servicing, assembly, and manufacturing. And from this, our 3 big mission operations are to dock to Swift, mount the auxiliary battery, and seal the battery. This will be done through autonomous rendezvous, autonomous battery connection, and autonomous epoxy curing process.
The following slide highlights some of Team PRISM's most innovative ideas from the 3 preliminary concepts that we developed. First, we wanted to utilize pads that imitate the natural setae of gecko's feet, which we'll use to attach and detach from objects. Second, we wanted to develop or use technology similar to a stud welder, which would basically involve us attaching studs onto the umbilical port and then mounting the auxiliary battery. And then third, we wanted to utilize epoxy to attach the battery to Swift.
Okay, so the storyboard of macro operations basically gives us a visual of all of the top level mission sequence actions here. So to begin, we're going to launch from French Guiana on the Ariane 6 rocket up until an altitude of about 600 kilometers. We're going to insert directly in the Swift's orbit just to make this as simple as possible for us to rendezvous with Swift. From there, we're going to use cold gas thrusters to initiate a rendezvous to meet up with Swift. And from there, we're going to get into the micro operations processes, but more on that in a minute here. So it's going to be all of our payload operations. Once those are deemed successful, we will separate from Swift and we will deorbit back to Earth. So as you can see on screen right now, this is our storyboard of micro operations. So once we rendezvous with Swift, this will be all of the small actions we take to directly interface with it and restore power to Swift. So to begin, we're going to extend our robotic arms. These have those CT gecko grippers attached to the end, so we can apply a force to the end of any surface, and we'll be able to adhere really well to use it as a gripping surface. So we'll extend the arms out, grab the battery pack. From here, we'll detach it from the payload. There's 2 locking hooks on the payload frame that'll keep the battery in place and protect it from launch vibrations and also from this rattling around too much during any sort of operations here. So those will disengage. We'll orient the battery with Swift's umbilical port, and we'd like to emphasize that at this point in the operations, inserting this into Swift, our battery pack, is kind of just like inserting a USB into a USB drive. It is very non-invasive and is built around Swift's already existing hardware to supply charge back to Swift and restore power. And so this will be done with the attaching battery process you see at the last frame there. And at this point, we'll extrude epoxy and get a flush finish to keep it connected to Swift. And we will apply shear force and disengage the gecko's feet. And then from there, we'll continue on with the micro operations, such as the separation and deorbiting. So it's the animation. As you can see in the animation here, first, like we just went over the micro operations, extend the arms, we'll grab the battery pack, detach it from the payload, and then from there, we'll move forth, plug it in the Swift, and at that point, we'll just extrude the epoxy, and hopefully it'll stick like glue for the rest of the whole mission sequence.
So for the autonomy and operations, we have primarily 3 different sets of autonomous actions. Have autonomous rendezvous with Swift, where we approach Swift from the injection orbit and match the orientation of Swift autonomously. Then we have autonomous battery attachment and docking with Swift. So we have 2 cameras on each arm, and each of those cameras have vision processing systems to analyze and recognize the battery pack and where it needs to go. And we have LiDAR systems on each arm for proximity detection of how far away we are from Swift. We also have autonomous epoxy curing using a PCB on the battery pack itself with 4 heating coils and temperature detection and modulation, which all happens autonomously.
All right, so let's go ahead and do an overview. They can be seen on the right-hand side. This is a CAD model of our payload, and we were able to fit it within the volume constraints stated within the RFP. Our payload has a length of 27 inches, a height of 17 inches, and a width of 16.4 inches. And as it can be seen, we went with a light, sturdy structure that conforms to that volume constraint stated in the RFP. And that's a truss structure kind of layout we decided to go with. We'll get more into the structure in a few slides here. We have 2 robotic arms on board. They are strong, maneuverable, and both of them fit within the power and mass constraints that were stated within the RFP. And then for our command and data hailing stuff, once again, like Sune said, we have integrated LiDAR, we have cameras and other things to control and monitor the movement of the robotic arms during our operations and our mission timeline. Finally, on the back end of our payload, we have our battery pack, which is shielded, and it's within our mass constraint, stay within RFP. It is capable of Swift, and again, also in the volume constraint. And at the bottom of the slide here, we have a 3-view wireframe 3-view of our payload, which we're going to go more into on the next slide. So this is our 3-view of our payload. We have the side view, top view, and the front view. On the left-hand side, we can see the side view where we get a good look at the 2 gecko hand pads that will be attached, 1 for each arm. There will be 4 pads for each of these gecko hands that will be used to grab the battery pack, and the other one used to grab Swift. We also have a little bit of a view of the truss structure. Again, we'll get a better view of it on the next slide where we talk about the structure. And then we have a side view of the auxiliary battery pack. Then in the middle, we have the top view, which we can clearly see the arm mount, which keeps both the arms mounted to the bottom base plate of the structure to keep it secured throughout the entire mission. We can also see both robotic arms that are on each side of the payload. And then finally, on the right-hand side, we have the front view, which we have a clear view of the battery latch mechanism that will hold the battery in place until we are ready to detach it and prepare attaching it to Swift. We also have a clear view of the umbilical port that is capable with Swift that will allow our connection. And finally, it's a little hard to see, but at the very bottom of the payload, we have thermal louvers, which will be there to emit radiation away from the payload. All right, so let's go ahead and take a look at the structure of our payload. So like I mentioned earlier, we decided to go with a truss-styled kind of layout for our payload. The top end of it has truss links, which are good for strong structural support at launch. They are lightweight. They are thick, hollow, 1-inch diameter pipes, which is excellent for the high strength and also low mass density, so we can stay within our mass constraint, stay within RFP. We then did a material trade study for our payload to decide a material that would be best, and we went with 4 different options. We looked at magnesium alloy, aluminum 6061 alloy, beryllium, and stainless steel. And we had 5 different criteria looked at, which was mass density, thermal conductivity, stiffness, strength-to-weight ratio, and factor of safety. After looking at all these options and ranking the criteria, it was found that beryllium would be the most suitable material for our structure. And this is due to its high strength values as well being less dense, which again helps with staying within our mass constraints. The material also has a high stiffness, which is really good for handling launch conditions and the rest of the mission operation. And finally, on the left-hand side, we have a better view of just the whole structure, a CAD model of the structure. We can see the hollow pipes, the truss links that are on the top, and we have 2 truss links on each side for better control of the shear forces. There's also a base plate at the bottom, which is helpful for keeping the arms mounted at the top end of it, and the thermal louvers will be at the bottom end of that base plate. And then there's a front base plate for bus connection.
So kind of the crux of operations 1 and 2, the robotic arms, we had to determine the sizing of them first and foremost. And the way we went about doing this was referencing some of the press kit information and reference images that Swift has available to the public. And in doing so, we figured out we needed a total wingspan of about 3.5 feet to reach from our point of contact on Swift to where the umbilical port is. To articulate these arms, we decided to go with some Cole Morgan AKM1 brushless DC motors. Brushless DC motors are pretty commonly used for space applications. Under max load, they'll consume 300 watts of power. And to ensure that we're not using anywhere near that much power during the operation, we're going to gear them up with a ratio of about 3 to 1, just to make sure we can get to that target 2 newtons of applied force on the battery pack to make sure we can move it around as we see fit. One of the goals that we had with these arms was to make sure that it was, once the operation was done, you could never really tell that PRISM was on Swift at all, apart from the battery pack being there. So that's why we went with the Gecko gripper pads. They're a passive adhesion, a method of adhesion that's currently going under a lot of development right now. They make use of weak intermolecular forces, London dispersion forces, to adhere to most any surface. And the way that you can remove them is by simply applying a little angle change to the seat A that messes with their interaction between the surface interaction between the seat A and whatever you're grabbing onto, and it allows it to break loose pretty freely. So for the command and data handling system of the payload itself, we're using a centralized architecture through the host spacecraft. We're going to use a radiation hardened processor and circuitry. We're using the RAD 6000 processor. The sensor data and the commands for the subsystems all run through this centralized architecture to the processor. And the other systems we have is we have a PCB for our battery bracket itself, which is Arduino based and has control of epoxy extrusion and curing with temperature control, like we mentioned before, with 4 heating coils made of copper, which will change the temperature accordingly to cure the epoxy. We also have robotic arms on our payload, which also need command data handling. So we have 2 cameras on each arms, which we chose Crystal Space Cam 1Us, which are radiation hardened. And each of these cameras also have vision processing systems to analyze where the battery bracket is and how we will attach to it. We also have LiDAR system for distance analysis, how far away we are from Swift. And for that, we use the ASC GSFL 16KS. And on the following slide, we have a command and data handling flowchart of all the commands and data that's going to roll through our system from the ground station and throughout everything else.
And then now we have the crux of Operation 3, the external battery pack. This is what's going to be supplying the power to Swift through its umbilical port. And this was designed in conjunction with the power subsystem. And what they did was they determined through trade study what cells we went with. We ended up going with some 55 amp hour lithium ion cells from Eagle Pitcher. These are great for us because Li-ion is commonly used today in industry. And they far outperformed Swift's current 80 amp hour nickel hydrogen battery that they have on board. We're having a total of 4 of these cells, 2 in series, and we have 4 just for redundancy. The material selection for the battery pack itself, we went with beryllium, copying the structure subsystem just because it's light and very thermally conductive. We're going to go with pyrogel for the thermal insulation for the epoxy curing process. This is a fairly new material, but it's very light and it's very performant. And then high density polyethylene for radiation shielding. This is what NASA uses on the ISS. So it's got plenty of heritage. And if it works for them, it'll work for us just fine. The epoxy we're going with, so the point of the epoxy is to make sure the battery stays within the umbilical port. We went with a Loctite EA 9690 Aero epoxy. It worked great for us. It plays nice with electronics. It doesn't outgas, and the curing schedule was perfect for our use case. And to cure that, like we've mentioned before, we're going to use some heating coils around the epoxy extrusion ports, and we're going to use the BCM and PCB on board to not only monitor the output of the battery cells and make sure they're not fully discharged at any point or fully overcharged, but to also monitor the curing process and make sure that we're doing that to spec. And here you can see kind of a crude schematic of the layout of our battery pack. The orange blocks are the cells themselves, and 2 will be wired in series in 2 groups total. Like I said, this is for redundancy and puts us over the 80 amp hour mark that Swift has been rated at. You can see our anchor holes as well, the epoxy reservoir. And we went with this simple layout just to make sure that if we wanted to modify this structure for any satellite in the future, it could be easily modified and manufactured to any required spec for any mission parameters. The umbilical connector is underneath the battery pack. That's why we did it in dotted lines. But the shape of that is something that we pulled from Swift's press kit as well. So the next slide here, you can see kind of our bill of materials and our mass budget for the whole payload. We decided to roll these both into one, and there's not too much to say about this other than that we are within the RFP pretty handily.
Looking towards the integration with the Venus class bus, these are subsystems that we expect the bus to handle also. Thermal wise, we're expecting our temperatures to sit around 40 to 80 C to not damage our servos or any electronics. For GNC, we're using gyroscopes paired with star trackers for precision altitude determination. We're also using reaction wheels for pointing accuracy provided from Blue Canyon. For CDH, we chose a RAD 6000. It's a radiation hardened processor that has a lot of flight heritage. For propulsion, we're using those nitrogen gold gas thrusters we mentioned before due to their low power draw, and we're expecting needing a total delta V of around 220 meters per second with an estimated propellant mass of 33 kilograms. And when we're choosing our class bus, we chose the 440 watt array bus because we expect to only utilize around 372 watts of power.
On this slide, we can see a table that shows the power allocated to the different subsystems of the spacecraft and the payload. The table was generated with info and equations from the Elements of Spacecraft Design book. On the right-hand side, you can see the Eclipse calculations, and on the left, you can see all the values out of Eclipse. From SCCRAM, we found that we'd spend about 8 hours in Eclipse and 15 hours out of Eclipse. These calculations include a 20% error margin. This ends up giving us a total of 372 watts, which allows for us to have an additional 72 watts for error and battery charging. This validates that we fit within the RFP constraints.
So for the bus data handling and comms, we decided to go with a ground station of Malindi Ground Station, which is the same ground station that Swift uses for this mission. So we will not need any real-time downlinks or observers or operators. We'll just have a downlink and uplink at the ground station. The requirements for our communication system is that we need to use S-band communication because Malindi Station only transmits and receives data and commands from the S-band frequency. And we have two links, uplink and downlink, where uplink will be for updated attitude data of Swift, and the downlink will be of the data dump, which we all showed in the flowchart before. The uplink margin, which we calculated using the SMAD spreadsheet, was 34.3 dB, and the downlink margin was 34.58 dB. And our data rate was 120,000 BPS. So this all validates that we fit within the mass and power constraints as well.
That's it.
Keep going.
Sorry. Looking at our risk on the left side, we have a table of all of our risks. On the right side, we have a risk matrix where we can see where the associated risk was before the mitigation plans in red and after mitigation plans in black. Our first one was our actuator stopped working, so our momentum wheels, and our mitigation plan for that was to have more redundant momentum wheels for the GNC system. Our second risk was camera failure. It's going to be due to exposure, radiation, or unforeseen damage from launch. The mitigation plan for this to have a backup camera included in the wrist of the arms, and since cameras are radiation hardened, only one should fail at a time. Our third risk is improper data dump at link. So this is from our CDH system. Our mitigation plan for this was to just have a really high margin of bits per second and a really high margin of dB. Our fourth risk is our bimetal springs stop working for the thermal louvers. This can be caused from vibrational forces to the launch, and our mitigation risk for that was having multiple springs. Our fifth one was a battery puncture or any damage towards the battery, and our mitigation plan for that, as mentioned before, was included a redundant battery. And our last one is for VCM failure caused by mostly bit flip or computational errors, and our mitigation plan for that was also a redundant VCM.
The following slide shows three limitations if improved could better support servicing missions like ours. First is battery energy density. We think that if batteries had higher energy density, we could use them on more missions where we would have to use less cells, meaning reduction in weight. Second is most satellites don't have a standard port meant for servicing. So if more satellites in the future have standard ports and docks, we can utilize the PRISM mission to service those satellites. And third, we would like to have more advanced and lightweight robotic arm. If the arm could be lighter and the motor where it could be more efficient, we could have additional power and mass available.
So a little bit of behind the scenes here. We experienced a few issues throughout this project, most notably being some workplace fluctuations. So we had to restructure the amount of work that everybody was doing at a time. And then we also onboarded a new teammate through this semester. So once again, we had to get them caught up to speed immediately so they could be working on the project just like that. And also to restructure all of our work again to now accommodate for having the full team back together pretty much. And so secondly, we had some mass issues originally. So the robotic arm motors and auxiliary battery pack were a bit too heavy. Initially, the robotic arms were made of Ti64, so just a titanium alloy. And we revised that to be made out of aluminum 6061 T6 and some carbon fiber reinforcement to accommodate the amount of strength and stiffness we need in those arms. And for the battery pack, we just reduced the size it had. So that involved removing some of the inside cells, but we still were able to provide a sufficient power to the payload, or not payload, sorry, to Swift while maintaining the mass budget. And lastly, we were concerned with the attachment of the auxiliary battery pack to Swift and how we were going to do this while making it non-intrusive and also having it stable and flush with Swift's interface. So that involved having the epoxy extrude at two places instead of just one. So now we have kind of like twice the chance of getting it flat instead of having just come out of one place and becoming a little bit of lopsided.
So everything we talked about today is summarized in our paper with the key elements shown here. Path to PDR, I mean, we really told you that the comms, propulsion, and GNC is all handled by the bus. We know from Blue Canyon's technologies, public press releases that it does have these capabilities. So our next steps is to create an FEA and thermal model of the entire payload bus system for analysis. Then we want to develop a one-to-one prototype for testing. And then based off that testing, we want to redefine the design based on any kinks and errors we find with the prototype. So kind of wrap things up, PRISM has a very important impact on ISAM. We can extend the lifespan of an older satellite while meeting all the requirements stated in the RFP. And while we talked many times about Swift during this presentation, this is easily modifiable for other customers. The battery pack is manufactured in a way that it can hold 4 cells, it can hold 8 cells, it can hold 12 cells. It's easy for a different target satellite in mind. Some of the innovations from this, so one of them was the non-intrusive battery installation. Instead of setting a payload up and awkwardly having to cutting to a satellite to rewire a battery, our non-intrusive method allows for just easy attachment of the battery and has a secondary source of power. In addition, our non-destructive docking and grabbing method basically leaves no trace of PRISM here, and it keeps the current satellite operating smoothly. So some of the lessons learned from this design process of producing a payload, and also the value of systems engineering, where you could develop the best arm in the world, but if it breaks mass budget, breaks power budget, it's useless. So a lot of that came down to collaborating teamwork between a bunch of different subsystems to make sure that it works with everybody's other subsystem, make sure we're not stepping on anyone's toes. So based on our collaboration and teamwork, Team PRISM has developed an innovative in-orbit servicing design that extends a satellite's lifespan with an external battery attachment. This will revolutionize ISAM through the next decade, allowing older satellites to be used in orbit for a longer time period and reducing the amount of space debris in orbit. With that, do we have any questions?
Okay, let's open it up to the judges for questions.
Any questions?
I guess he answered everything along the way. So I guess that question I would ask is what do you like if you go back to your lessons, the tech gaps, actually, like, because I really like what you had in the tech gaps. Yeah, like, so specifically for the standard ports for servicing, like what would you see be included on that standard port? Like what elements?
We kind of hope that there'd be better fueling opportunities. So we don't want to just limit ourselves to just replacing an auxiliary battery. We also want to have the opportunity to maybe, add more propellants, add more fuel, or overall like add more batteries. So having a standard port that can let us do any of those 3 things would overall just improve the satellite and mission lifespans. I also believe the potential for like hot swappable batteries as this technology becomes more prevalent in the industry would really do wonders for the mission at hand here.
Do you have any other questions from the judges? Okay. Thank you, Team PRISM, and we'll round up and we'll start the last team for today in about 2 minutes. Okay, I think we can get underway. This will be the final presentation for the first day of the final showcase, and this is Team RADFAB from Arizona State University. Guys, take it away.
Hello, can you guys hear us?
Yes. Yes.
Okay, coolio. All right. So, hello everyone. We are Team RADSAT. We're presenting the RADFAB. My name is Nico.
My name is Nathan.
My name is Neil. Next slide. So today we're going to begin with our mission concept and requirements, then our core technology, followed by an overview of our ConOps, then finishing with the mission feasibility and the timeline. So beginning with the overview of the mission concept, participating in the Consortium for Space Mobility and ISAM Capabilities, known as COSMIC, the project required the identification of shortcomings in the development of ISAM capabilities and subsequently the conceptual development of technologies to address them. Our core technology, RAD, a solid-state bonding technology, is relatively high TRL that predates this project, and as such is omitted as a key innovative idea. We will instead highlight the SSCC tool, a RAD derivative technology that bonds ceramic particulates to a wire substrate, our optimized 4-axis motion system for the toolhead, and a satellite flat packing standard that serves to broaden the types of satellites that could be orbitally assembled by RADFAB. The tyranny of the fairing, weight limitations, and other constraints imposed upon satellites by launch vehicles or Earth conditions rather than the space environment continue to be areas in need of improvement to further ISAM initiatives. These Earth conditions lead to satellites using risky deployables for critical systems like solar arrays, for example. We aim to create a solution to plug the gaps existing in ISAM by paving the way for larger, more reliable orbital fixtures. Our initial RADFAB concept was a purpose-built solar array assembler, as shown on the right. However, we believe that our goal should be a platform capable of end-to-end satellite assembly, rather than just replacing a deployable like solar arrays or radiator arrays. Per the spider-like picture on the left, we were aware that a more general-purpose system would need to be capable of locating our tool and workpiece, and as such, a mature RADFAB system would utilize 2 arms to move the system and a single arm to move the tooling during operation. Early in the design iteration process, we were inadvertently limiting the scope of our project, and that's a challenge that we continually grappled with, which was moving away from a production mindset and more towards an systems engineering mindset. We sought to address this identified area of need by first developing a design reference mission for what a mature RADFAB should do. This took the form of a satellite capable of autonomously assembling an IOMOS satellite from flat-packed components. RADFAB would then be launched, it would unpack these IMOS components, and then it would assemble, wire them together, and then deorbit. To pave the way for an ambitious IMOS mission, we are performing a scaled-down mission, validating each of the key components and evaluating key performance metrics. We will instead launch a self-contained scaled-down version, which will assemble test builds, and after a 1-week exposure period to low Earth orbit conditions, we'll conduct various tests to evaluate the performance and viability of the assembly methods. To further develop this concept, we next had to define our mission requirements. Chiefly, the system must be capable of adequately demonstrating the viability of our innovative technologies. The system must also operate autonomously within reasonable limits. Human-in-the-loop processes remain a standard for both orbital and terrestrial robotics applications, and to ensure mission success, it remains the current standard for RADFAB as well. Environmental considerations are pretty straightforward. We expect our system to operate within normal low Earth orbit conditions. Following the environmental considerations, the envisioned system must be payload ready for a BCT XSAT Venus class bus, necessitating that the system's mass and physical dimensions were well within payload capabilities, as well as ensuring that the maximum power draw of our system would be within that supplied by the satellite bus. Next, Nathan and Neil will discuss the linchpin technologies that enable the RADFAB system.
What is RAD? RAD stands for Resonance Assisted Deposition, which uses piezoelectric transducers to convert ultrasound into oscillatory mechanical energy, When these oscillations are applied directly to a material, it causes vibrations to propagate, reducing the material's static stress, inducing acoustic softening. The tool head also applies static compression and the localized static stress inducing acoustic softening. The tool head also applies static compression, and the localized low amplitude shearing off material under the tool initiates bulk transfer, creating a bond, much like friction stir welding, with the advantage of minimal heat being generated. Applying this in linear steps allows the RAD tool to function similarly to fused filament fabrication systems.
Excuse me, we have a video here. Could you go back to the previous slide? We had a video. Could you please play that? Thank you.
Is the video not working?
Yeah.
All right, thank you. It's fine. We can.
All right, we can go to the next slide.
If you want, you guys can pull up your slides in case we run into that again, and we'll switch over.
Yeah, I mean,
Okay, yeah, because we have a couple other videos in our presentation. Is it okay if we switch right now?
Go ahead. We'll give you an extra minute.
Submitted the share request.
Go ahead and get the PowerPoint up.
Should be good to share now, so try again.
Okay,
awesome. Thank
Can
you.
you see it?
All right. Unlike FFF, RAD's greatest strength is that it is fully solid-state process with no thermal history or re-solidification issues. RAD can be used as both an additive manufacturing process and as a cold weld process, creating fully homogeneous bonds. It is a highly energy efficient method and attractive for space applications. It poses no safety or environmental hazards and can bond aluminum with copper, zinc, or titanium. We have demonstrated both butt welds and made tensile tests, as well as exposed RAD in a vacuum chamber. It is also worth noting the versatility of the RAD toolhead. We've currently implemented the technology in CNC machines, traditional FDM chassis, robotic arms, holonomic drive systems, and it has shown the capability of converting loose granules back into feedstock.
To facilitate the use of insulated wires in RADFAB, we have a secondary solid-state ceramic consolidation tool, or SSCC. This tool applies the same effect as the RAD tool around a wire to bond alumina particles to the wire surface, creating a strong insulative coating. RAD operates at a much lower energy on the same timescale as many alternative technologies. Additionally, RAD neither generates nor imparts heat into the workpiece. We also performed a trade study on our capabilities of using alumina-coated wires for insulation, finding that alumina offers a strong insulation option for a lightweight in size. To determine the feasibility of RAD bonding versus conventional adhesives for electrical and structural bonds, we performed a trade study on space heritage adhesives. The main advantage of RAD is the elimination of weight, as it can directly bond to structures homogeneously.
During the conceptualization of a mature system, we knew that robotic arms would be necessary for locomotion, workpiece, and tool positioning. As such, we compared space heritage robotic arms to determine what our device would need to accomplish this. We evaluated the weight, energy consumption, and degrees of freedom between 4 robotic arms, and we decided that a mature RADFAB platform would utilize the ERA robotic arm for locomotion and workpiece positioning. Next, we're going to be going over the key components of our payload. The enclosure is the rigid structure that houses and protects our electronics and machinery, as well as enables the interfacing between our payload and the satellite bus. The robotic motion control is handled by a radiation-hardened Duet MB6XD CNC control board with a radiation-hardened Raspberry Pi Astro serving as the dedicated processing unit. The 4 ISOSpace omnidirectional antennas provide ample signal coverage, with the ISOSpace S-band transceiver encoding and decoding information sent or received through the antennas. For power management, we added a supplemental 28-volt 14.3 amp-hour battery to enable high-voltage operations for an extended duration, as well as a power supply to convert between the needed 12, 24, and 120-volt power inputs. The ultrasonic waveform generator is a software-driven waveform generator that outputs electronic sine waves. The 60 kilohertz waveform is then relayed to the RAD and SSCC transducers, driving the piezoelectric actuators, inducing low amplitude, high frequency vibrations in the tool heads. And then here you can see a blown up version of the model, which removes the electrical components, as well as the wire spooler and the omnidirectional antennas. The x-axis gantry moves the robotic arm in the x-axis for large, fast movements, with the z-axis rails moving the entire bed and consequently workpieces in the z-axis.
To allow RADFAB to locate, picture, and perform RAD processes on workpieces, we designed a combined 4-axis motion system based on a SCCRAM industrial robot design. This maintains a high Z rigidity relative to its weight and size, making it ideal for our process. A fixed gripper allows for gripping and locating of our test pieces. To better meet the friction and weight concerns of the space environment, the system is fully direct drive and can utilize space heritage components as drop-in replacements. Though our trade studies highlight a more complex arm design with 6 degrees of freedom as optimal for a larger mission, we identified that one of the primary design challenges would be to limit the complexity of the system to ensure reliability, leading to this 4-axis system being favored instead for this demonstration mission.
And then this is just a very quick video which demonstrates all axes of motion in the RADFAB. The tensile tester doubles as a workpiece fixture, holding the tensile coupon in place during the rad welding of the 2 strips. And then after a 1-week exposure period, it then applies tensile stress to the coupon, and an integrated load cell will record the load applied to the coupon. And then this is just a very simple visual operation of the gripper picking up and then moving the tensile bar into the tensile tester.
The RAD fabrication tooling consists of our core technology in which the RAD method is mounted as the end effector of the SCCRAM arm. The RAD tool head will take a 24-gauge wire driven by our wire extruder and cutter system. The RAD tool head will also resonate at 60 kilohertz. This is the RAD tool in action across our test builds, where the wire will be fed through a guided tube to the SSC tool. The solar tester also doubles as a workpiece fixture, holding in place the 2 solar cells during trace laying and then enabling the UV light and performing standard solar array tests to demonstrate proper electrical connection between the 2 solar cells. And then this is just the solar cell holding the workpieces during trace laying and also showing the UV lights being enabled.
The SSCC tool itself is contained in a compact inline unit, taking the wire from the Bowden tube and a tube of alumina powder. This powder will be fed using a powder auger, which uses sonication to help flow the material as the auger contracts. It also serves as the storage for all the powder required in the mission, eliminating the need for a separate storage vessel. A short representation of the test build demonstrates how powder auger contracts, feeding powder to the SSCC tool for coating.
The scientific instruments serve both data collection purposes, but can also be used for troubleshooting in the event of a system malfunction. The electrical conductivity sensors detect wire breakage in the RAD feedstock, evaluate the electrical connections in the wire laid across the wire mounting points, and are also used to evaluate the connections between the solar cells. The first load cell is in the tensile tester and detects the load applied to the tensile coupon, and then the second of our load cells sits just above the RAD tooling and collects compression data for PID control and tuning of the RAD process. And then the optical cameras serve the purpose of troubleshooting and also superficial test build analysis. There are IR sensors to track the various transducer temperatures, as well as the temperature of the RAD toolhead itself, and multiple thermistors monitor the heat of the various mechanical and electrical components within the system.
RADFAB operates on a human-in-the-loop controls process, requiring regular contact with ground control and verification between steps, ensuring reliability and safety of the mission. To facilitate this, our motion control mainboard and our single board computer will be logging telemetry from sensors. Certain necessary telemetry data will be sent at regular intervals, and additional telemetry can be requested by the ground station, where it will be sent from the SBC storage. The ground station is also capable of loading new or modified test build operations by uploading a G-code file, as well as changing machine configuration parameters as needed. We utilize a high data rate transceiver to modulate and demodulate signals to send to our omnidirectional antenna array, minimizing chances of being in an antenna dead spot. To further minimize risk of communications failure, we will be operating in the UHF frequency range. In emergency failure of UHF communication, we will attempt to operate on VHF and SHF ranges depending on geocentric location as well.
And then for our concept of operations, we decided to make an animation of the operations that RADFAB will perform. So for test build 1, it starts with the grippers picking up the tensile test coupon and positioning it within the tensile tester slot. The RAD tool then lays a 24 gauge wire across the weld joint, bonding the two halves of the tensile coupon together. For test build 2, the RADFAB tooling moves to position itself over the solar cell workpiece. And then it begins joining the two solar cells together and the trace laying operation as well. Following the joining together of the solar cells, the UV lights are then enabled and a standard solar array test will be performed. And then for test build 3, the alumina is pumped out of the powder hopper and then lays a ceramic coated wire that is acoustically bonded to the two aluminum wire mounting points. Following a successful assembly of the test builds, RADFAB will then perform an initial evaluation and then enter a 1-week hibernation period. After the hibernation period, a comprehensive analysis of the test build will be performed, evaluating the tensile strength of the weld joint and the electrical connections between the solar cells, as well as the installation of the alumina-coated wire laid between the two mounting points. And then now onto the practicality of our mission.
The TRL rating of our critical components begins with the SSC at a level 2, since the concept has been developed but needs to be proven. The RAD tool is at a TRL 4 as the technology is developed but not tested in space or space-like environment, while the powder feeder and SCCRAM arm are at a TRL 7 since these components are off the shelf and have been tested in space environments.
To verify our payload can survive launch forces, we perform computer simulations. As SpaceX is currently the leading domestic launch provider and our payload and mission are largely launch provider agnostic, we based our criteria on their rideshare guide. Illustrated here are some of the analyses that we performed on our RAD motion system. As SpaceX recommends, our tool motion system can tolerate up to 10 G of axial force and 17 G of lateral force, which we are applying in the worst case direction as we determined by lower fidelity simulations. Our higher fidelity submodel analysis does indicate a low frequency natural mode on one structural component, which can be addressed by changing gusset design. Analysis of our Z motion system in bed assembly shows that the rails used are insufficiently rigid for launch forces and create 3 natural frequencies below the acceptable 40 Hz minimum. This can be rectified by increasing the diameter of these guide rails. Analysis of our enclosure shows that we may need to add additional bracing to the frame to prevent buckling of the panels. No other further components revealed problems with launch conditions. Overall, these modifications are minor, and our analyses prove that our core design can be made launch capable with minimal work needed. Performing accurate FEA was one of the significant challenges of our design process, as our payload has many structural sub-assemblies, and ensuring we captured accurate loading conditions on each part was a significant learning experience.
Following that, this is our bill of materials and calculated mass of our subsystems, including all the fasteners. Our payload is currently under weight requirements by 8 kilograms, providing ample room in our weight budget to implement the reinforcements in our design.
Outlined are what we believe to be the most pertinent risks to overcome in the realization of a mature RADFAB system. Welding failure and tool breakage can be non-starters, as these are critical pieces of the process. These issues have been documented and mostly resolved, and we expect further improvement going forward. The other main failure mode for RAD in vacuum operation is overheating of the tool and transducer, which brings the tool's resonant frequency out of operation conditions and can induce a change in piezoelectric effects, leading to dielectric breakdown. Developing efficient heat removal methods for RAD tools is currently an active area of development, so we expect this to be mitigated within Cosmic's expected timeline. Other risks include more generic space system risks like electronics-related failures and motion-related system failures, which have been successfully mitigated or managed by space missions in the past.
We believe that once the RADFAB system is assembled, we will need 2 years of payload integration, ground testing, and flight readiness evaluation. Following that 2-year period, RADFAB would be launched into low Earth orbit. The system would perform an initial systems check and then begin assembling the test builds. Following the test build assembly completion, RADFAB will enter a period of hibernation for 1 week to evaluate space condition exposure on the test builds. Then the solar test and tensile tests will be performed, and then following a successful mission, RADFAB will be decommissioned into the orbit.
The Cosmic C3 project enabled us to create complex animations and simulations of multi-level parts and assemblies. We learned extensive space and aerospace requirements and technologies while leveraging NASA Systems Engineering Handbook. We would like to further develop RADFAB by creating more extensive space simulations, optimize some mechanical designs, further developed our IOMOS concept, raise the TRL of RAD technology with extensive payload development projects. We would also like to extend auxiliary technologies such as scaling up the RAD system, have integrated cooling systems on the transducer, and extending the multi-level material capabilities through braiding or twisting of similar or dissimilar feedstocks to create superstructures. We're highlighting these 3 technologies because these are the ones we are most personally involved in, but there are many other active areas of RAD development as well.
In all, RADFAB is an ISAM platform that aims to eliminate satellite constraints imposed by the launch vehicle, eliminate the need for risky deployable systems, reduce the weight budget allocated to adhesives, and pave the way for larger ISAM missions in the future. We would like to thank the excellent support of our mentor, Ryan Benson, our professor, Dr. Keng Xu, as well as the rest of the Future Manufacturing Research Lab.
Hey, thank you. Do we have questions from the judges? So if there was one of these, I will ask, but one of the technologies you need to improve, which of those are essential, or to put it another way, in order to enable this, which non-core technologies would you like to see improved?
To enable this mission, we wouldn't need it, but for the development of our mature concept, where we could entirely develop a satellite from start to finish, we would need to see some improvements in machine vision technologies and, in general, robotics technologies to enable better robotic motion for something very large scale. For our current mission, we believe that outside of our core technologies, everything could be done feasibly today as well.
Maybe a related follow-up question. What's the biggest risk or technology hurdle you see for doing an in-space demo versus what you could do on the ground with this setup?
So that would be heat. Actually, if you don't mind, we would like to go back and show that video that we didn't have, or it wasn't played. So this here is a vacuum test of the RAD system. We actually performed this test, and what the biggest challenge here is that after about 10 to 15 minutes, the tool, even though the tool isn't deposited, there's no heat in this process as a critical piece. Just the fact that we are putting electric signals through it and creating mechanical vibrations does eventually heat up the tool. On Earth conditions, we have no issues with this. We can use fans and just general atmospheric convection to remove the heat from the tool. In space, this is a bigger issue. And since we can't physically add a lot of mass, like thermal mass, to the tool, since it's a mass dampener system, we have to create some different solutions to manage the heat on that, which we are working on right now.
Copy. Thank you.
Do we have any more questions from the judges?
Yeah, I have a question. Can you go over the risks again, like how you plan to mitigate risk? I couldn't quite understand it well.
Yes. So for test piece positioning errors, this is where something in our robotic motion system has not positioned the tool properly. We have optical cameras as well as other sensors to allow for manual ground intervention. We can also, because of the Duet MB6XD CNC control board we're using, we can manually operate our system to restore the test piece into the place we need it to be.
Yeah, you don't have to go through the whole thing again. I was just wondering, because you wrote like a mitigation plan for each of these, and I haven't read your paper, but in your paper, do you go through each of these to explain, like kind of expand what you plan to do with the mitigation plan?
Yes, we have.
Okay, thank you. I'll just go to that. That's fine. Thank you.
Okay, do we have any more questions? Okay. Well, thank you again to our team, Team RadSat with their RADFAB system.
Thank you. It was a pleasure.
Thank you.
Thank you. I also want to thank all the teams who presented today, those who came here in person and those online, as well as thanking the judges, again, those here in person, those who joined online, and the other participants. You know, we opened this to the public so we can draw more people, and even your friends and family, because I know sometimes that's, well, we've all been there. I mean, the experienced professionals, it's like they want to know what we're doing. So I hope you felt free to share that, because I think every team here did a fabulous job. I don't know if any of the other judges want to add a word before we break. Okay. Oh, wait. Yeah, Jeff's gonna speak.
So Jeff Reber from Aerospace. I just wanted to echo the last thing that Jacob said. I think it's really impressive to see what all the undergraduate teams did. As a professional in this field for 20 years, there's some really innovative stuff, and what you guys are doing as undergrads is really impressive, and the teamwork involved. So thank you for the presentations I could make. They were fantastic.
Okay, so we're gonna break for today, and just to say the last thing again, there were 9 teams that presented today. I think all 9 are outstanding. I think some of you may have watched the other teams, and you always tend to think that everyone else is doing a better job, but that's because everyone did a great job. So no one should feel short if they think the other teams did better, because they're all great. So we're gonna break for today. If you're in El Segundo, we're going to do some lab tours. But for everyone else, we will be back here. I think we kick off at 8:30 tomorrow morning on the West Coast, 11:30 on the East Coast. And then we'll have five more briefings tomorrow. And then on Wednesday, the whole operation moves to NASA Goddard, except for the people. The people will not move across the country. And we'll have the last 9 on Wednesday. So thank you, everyone. And we'll see you tomorrow.